Hello, wonderful souls. Welcome back to another journey through the universe's gentlest mysteries. Tonight, we're going to discover something extraordinary. Something that connects the calcium in your bones to exploding stars, the iron in your blood to the violent death of ancient suns, and the very atoms of your thoughts to the first 3 minutes of cosmic time. Right now, as you rest your head on your pillow, your body contains atoms that were forged in the hearts of dying stars billions of years ago. The universe didn't just create you, it became you. And tonight, we're going to trace that recipe backward, ingredient by ingredient, until we reach the cosmic kitchen where everything began. If you love falling asleep to the soft voice of science, to stories that make you feel both infinitely small and infinitely connected, consider subscribing. And if tonight's journey touches something deep within you, a gentle tap of the like button helps us reach more dreamers like you. Now, let's begin. Imagine opening the oldest cookbook in existence, not one written on paper or carved in stone, but one written in the language of physics itself, inscribed in the fabric of space-time during the first moments after the Big Bang. This cosmic recipe doesn't tell you how to bake bread or roast a chicken. Instead, it tells you how to build everything: galaxies, planets, flowers, thoughts, dreams. It tells you how to build a universe. The remarkable thing about this recipe is its simplicity. Unlike a complex French cuisine requiring dozens of exotic ingredients, the universe started with just a handful of fundamental components: hydrogen, helium, trace amounts of lithium. That's essentially it. From these 3 elements created in the scorching aftermath of the Big Bang, everything else would eventually emerge. Think about that for a moment. The device you're listening to this on, the water you drank today, the neurons firing in your brain as you process these words, all of it descended from a recipe that began with just 3 ingredients mixed together in the ultimate primordial soup. But here's where the story gets truly magical. The universe wasn't content with this simple menu. Over billions of years, it learned to cook. It built stellar furnaces where pressure and heat could fuse those simple elements into more complex ones. It created supernova ovens where even heavier elements could be forged in the extreme violence of stellar death. The universe became a cosmic chef, constantly experimenting, constantly creating new flavors of matter. In 1952, a British astronomer named Fred Hoyle sat in his office at Cambridge University, wrestling with a profound mystery. Scientists knew that stars were hot, millions of degrees hot, and they suspected nuclear fusion occurred in stellar cores. But the mathematics didn't work. The calculations suggested that stars couldn't produce enough carbon, oxygen, and nitrogen to account for what astronomers observed in the universe. Hoyle became obsessed with this problem. He filled notebook after notebook with equations, exploring different nuclear pathways, different energy states, different possibilities. His colleagues thought he might be chasing a ghost. The numbers simply refused to cooperate. Carbon, the element that would eventually become the backbone of all life, seemed mathematically impossible to create in sufficient quantities within stars. Then came his breakthrough, one of those moments in science where stubbornness meets insight. Hoyle predicted that carbon nuclei must have a very specific energy state, a resonance that would allow the fusion process to occur efficiently. Without this particular energy level, carbon production would be impossibly rare. With it, stars could manufacture carbon in abundance. The prediction was bold, precise, and completely theoretical. Hoyle had no experimental evidence for this energy state. He deduced its existence purely from the fact that we, carbon-based beings, exist to ponder the question. It was a form of reasoning that would later be called the anthropic principle. We can deduce properties of the universe from the simple fact that we're here to observe it. When nuclear physicists tested Hoyle's prediction in the laboratory, they found the energy resonance exactly where he said it would be. The universe really did have a special trick for cooking carbon. This discovery opened the floodgates. If stars could create carbon through this elegant nuclear pathway, what else could they create? Over the next several years, Hoyle and his collaborators, Geoffrey and Margaret Burbidge and William Fowler, worked out the complete stellar nucleosynthesis theory. They showed how stars could build element after element, working their way up the periodic table through successive fusion reactions. Hydrogen fuses to helium, helium fuses to carbon, carbon fuses to oxygen, then neon, then magnesium, then silicon, and finally iron. Their 1957 paper, often simply called B2FH after the initials of its authors, revolutionized our understanding of cosmic chemistry. Suddenly, the universe's recipe book made sense. Stars weren't just balls of burning gas. They were cosmic factories, transmuting lighter elements into heavier ones, enriching the cosmos generation by generation. But even as this picture emerged, scientists realized they were missing something. The stellar recipe could explain elements up to iron, but what about everything heavier? What about copper and zinc, silver and gold, mercury and lead? What about uranium, the heaviest naturally occurring element? The answer would require an even more violent cosmic process. One we'll explore later in our journey. For now, though, let's sit with this remarkable realization. The universe learned to cook through trial and error, through billions upon billions of stellar experiments occurring over cosmic time. Every star that lights up the night sky is conducting its own version of the primordial recipe, fusing elements in its core, adding its own contribution to the chemical enrichment of the cosmos. Some stars cook fast and die young in spectacular explosions. Others, like our Sun, cook slowly and steadily, patiently working through their nuclear fuel over billions of years. And here's something that might make you smile as you drift towards sleep. The universe is still cooking. Right now, at this very moment, stars throughout the cosmos are fusing hydrogen into helium, helium into carbon, building the elements that might one day become part of some distant planet, some future form of life, some dreamer lying in bed wondering about their cosmic origins. The recipe of the universe isn't a fixed formula, executed once and finished. It's an ongoing creative process, a culinary adventure that's been running for 13.8 billion years and shows no signs of stopping. Every breath you take, every heartbeat, every synaptic firing is made possible by ingredients that were cooked in stellar kitchens long before Earth existed. Think about the oxygen you're breathing right now. Every oxygen atom in your lungs was manufactured inside a star that lived and died before our solar system formed. That star spent millions of years fusing lighter elements together, working its way up the periodic table until it finally produced oxygen in its core. Then it died, possibly in a supernova explosion, scattering its precious cargo of oxygen atoms into space. Those atoms drifted through the galaxy for perhaps millions of years, gradually becoming part of a new cloud of gas and dust. That cloud eventually collapsed to form our Sun and its family of planets. Some of those oxygen atoms ended up in Earth's atmosphere. And now, tonight, one of those ancient stellar products is flowing through your bloodstream, binding to hemoglobin, keeping you alive. The same story repeats for every element in your body. The calcium making your bones strong right now, cooked in stellar fusion reactions. The sodium and potassium creating electrical signals in your neurons, manufactured in dying stars. The trace elements like zinc and copper that enable crucial enzymes, forged in the extreme conditions of supernovae. You are, quite literally, a temporary arrangement of stardust, The universe cooked your ingredients over billions of years, assembled them into a planet, and then, through the even more mysterious recipe of biology, arranged some of those elements into the pattern of you, a being capable of contemplating its own cosmic origins. Can you feel it? That sense of connection to something vast and ancient? You're not separate from the universe, observing it from the outside. You are the universe, temporarily organized in a form that can think and feel and wonder. You are what happens when the cosmos reflects on itself. As you breathe slowly in and slowly out, you're participating in cycles that stretch back to the beginning of time. Your breath contains nitrogen forged in stellar cores. Your heartbeat relies on calcium from ancient supernovae. Your thoughts arise from patterns of atoms that have been recycling through the universe for eons. The recipe of the universe is written in your very existence. You are one of its most exquisite creations, not because you're separate from the cosmic process, but because you're an intimate part of it. The same forces that shaped galaxies and ignited stars also shaped you. The same elements that fill the vast spaces between worlds also fill the spaces between your cells. And here's the truly beautiful part. The universe's recipe isn't finished with you yet. The atoms that comprise your body will continue their cosmic journey long after you're gone. They'll return to the earth, perhaps joining the soil where new life will grow. Eventually, in the far distant future, they might even return to space, incorporated into some new stellar formation, recycled once again in the universe's eternal kitchen. So, as we begin this journey together, tracing the cosmic recipe from its simplest ingredients to the intricate complexity of galaxies and life, remember, we're not studying something distant and abstract. We're studying ourselves. We're exploring our own origins, written in the language of physics and chemistry, in the transformation of energy into matter, in the patient accumulation of atomic complexity over cosmic time. The story of the universe's recipe is your story. And it begins, as all great recipes do, with the gathering of ingredients, those first fundamental elements that emerge from the cosmic oven in the opening minutes of time. In the first 3 minutes after the Big Bang, the universe created 98% of all the normal matter that would ever exist. Everything else, every complex element, every exotic atom, every piece of the periodic table beyond lithium, amounts to barely 2% of cosmic matter. Those opening minutes were the most productive cooking session in the history of existence. And we're still living off what came out of that primordial oven. The universe's shopping list for everything that would ever be was surprisingly short: hydrogen, helium, and a trace amount of lithium. 3 ingredients. That's all the raw cosmic kitchen started with. And from this impossibly simple beginning, everything you see, touch, taste, and are would eventually emerge. The story of how scientists discovered this cosmic recipe is one of the most remarkable detective stories in the history of science. And it begins not with looking out at the stars, but with looking at them more carefully than anyone had before. In 1925, a young woman named Cecilia Payne arrived at Harvard College Observatory with a radical idea and the mathematical skills to prove it. She had fled England, where women weren't allowed to receive degrees from Cambridge University despite completing all the coursework, to pursue astronomy in America. What she would discover would completely overturn humanity's understanding of what the universe is made of. Payne studied stellar spectra, the rainbow patterns of light that stars emit, each pattern containing a chemical fingerprint of the star's composition. The conventional wisdom of the time held that stars were made of roughly the same mixture of elements as Earth. After all, the reasoning went, why would the cosmos be fundamentally different out there than it is here? But as Payne analyzed spectrum after spectrum, running calculations that filled hundreds of pages of notebooks, she began to see something extraordinary. The numbers told a story that contradicted everything astronomers believed. Stars weren't made mostly of iron, silicon, and oxygen like Earth. They were made almost entirely of hydrogen and helium, elements that were relatively rare on our planet. The implications were staggering. If stars were primarily hydrogen and helium, then so was most of the visible universe. Earth wasn't typical. We were the exception, not the rule. We lived on an unusually heavy element-rich world in a cosmos dominated by the lightest elements. Payne's doctoral thesis, completed in 1925, contained this revolutionary finding. Her conclusion was clear and backed by rigorous analysis. Hydrogen was approximately 1,000,000 times more abundant in stellar atmospheres than previously thought, and helium was nearly as abundant. Together, these two elements made up the overwhelming majority of stellar matter. But here's where the story takes a frustrating turn, one that reveals as much about human nature as it does about cosmic chemistry. When Payne showed her thesis to Henry Norris Russell, one of the most prominent astronomers of the era, he convinced her to soften her conclusions. He told her the hydrogen and helium abundances were almost certainly not real. Despite her mathematical proof, despite her careful analysis, Russell believed the finding was too radical to be true. So, Payne added a sentence to her thesis describing her own discovery as spurious, a word meaning false or illegitimate. She downplayed what would later be recognized as one of the most important discoveries in astrophysics. Her thesis was published with this self-contradiction embedded in it. Brilliant analysis leading to the correct answer, followed by a disclaimer suggesting the answer was wrong. 4 years later, Henry Norris Russell published his own paper reaching the exact same conclusion Payne had reached. Hydrogen and helium dominated stellar composition. The universe was made primarily of the lightest elements. Russell's paper was celebrated. He received credit for the discovery. Payne's pioneering work was largely forgotten for decades. It wasn't until the 1970s, long after Payne had spent a distinguished career at Harvard, despite being denied a formal faculty position for years because of her gender, that historians of science began to set the record straight. Cecilia Payne Gaposchkin, she had married and taken her husband's name, had made one of the most fundamental discoveries about the cosmic recipe, and it had taken half a century for her to receive proper recognition. But let's return to those primordial ingredients themselves, because their story is even older than the stars Payne studied. The hydrogen and helium that make up the universe weren't created in stellar cores. They're more ancient than that. They were manufactured in the aftermath of the Big Bang itself, during a brief window of cosmic cooking called Big Bang nucleosynthesis. Imagine the universe 1 second after its birth. It's unimaginably hot, about 10 billion degrees Kelvin. That's roughly 1,000 times hotter than the core of our sun. At these temperatures, matter can't exist in the forms we're familiar with. There are no atoms, no molecules, no chemistry whatsoever. Instead, there's a seething soup of fundamental particles: protons, neutrons, electrons, and photons, all bouncing off each other with tremendous energy. The universe is expanding rapidly, and as it expands, it cools. This cooling is crucial. Within the first few minutes, the temperature drops enough for nuclear fusion to begin, the same process that powers stars, but occurring throughout all of space simultaneously. Protons start sticking to neutrons, forming deuterium, heavy hydrogen with 1 proton and 1 neutron in its nucleus. Most deuterium quickly fuses into helium-4, the stable form of helium with 2 protons and 2 neutrons. Some helium-3 forms as well, along with tiny amounts of lithium-7. But here's the remarkable constraint. This cosmic cooking session has a very short timer. Within about 3 minutes, the universe has cooled and expanded so much that the particles are too spread out and too low in energy for nuclear fusion to continue. The primordial nucleosynthesis window slams shut. Whatever elements were created in those first minutes constitute the base recipe for everything that would come after. The ratios are precise and predictable. For every 12 hydrogen nuclei created, the universe manufactured one helium nucleus. Lithium appeared in trace amounts, only about one lithium atom for every 10 billion hydrogen atoms. These ratios weren't random. They emerge from the fundamental physics of nuclear reactions, the density of the early universe, and the relative numbers of protons and neutrons available. What's extraordinary is that we can still detect this primordial composition today, nearly 14 billion years later. When astronomers observe the oldest, most metal-poor stars that formed from clouds of gas that had never been enriched by previous stellar generations, they find helium abundances of about 25% by mass. Exactly what Big Bang nucleosynthesis predicts. It's like finding the original recipe card, slightly yellowed with age, still readable after billions of years. The cosmic proportions set in those first 3 minutes have persisted, serving as a fossil record of creation itself. Russian-American physicist George Gamow was one of the first to work out the details of Big Bang nucleosynthesis in the 1940s. He had a playful side. He once authored a paper with his student Ralph Alpher and added Hans Bethe as a co-author without asking him, just so the paper's authors would be Alpher, Bethe, Gamow, a play on the Greek alphabets alpha, beta, gamma. The paper became known as the AVG paper, and it laid the groundwork for understanding primordial element creation. Gamow and his colleagues predicted that if the Big Bang model was correct, the universe should have created specific abundances of hydrogen, helium, and lithium in predictable ratios. When later observations confirmed these predictions with remarkable precision, it became one of the strongest pieces of evidence supporting the Big Bang theory itself. But there's a cosmic irony embedded in this story. Gamow initially hoped that Big Bang nucleosynthesis could explain all the elements. He wanted those first 3 minutes to cook up everything from hydrogen to uranium. The mathematics, however, refused to cooperate. Beyond lithium, there was a gap. No stable elements with mass numbers of 5 or 8. The primordial cooking process couldn't jump across these gaps in the nuclear stability chart. This is where stellar nucleosynthesis, which we touched on earlier, becomes essential. The universe needed stars to build the heavier elements because the Big Bang alone couldn't do it. The cosmic recipe required 2 stages: the Big Bang to create the base ingredients, and stars to elaborate on that foundation. Think about what this means for a moment. The hydrogen atoms in the water you drink are the most ancient objects you'll ever encounter. They were created in the first minutes of cosmic time, before any stars existed, before any galaxies formed, when the universe was a hot, dense plasma cooling from its moment of creation. That hydrogen has been recycling through the cosmos ever since. Some of it has passed through stellar cores multiple times, fusing into helium and contributing to stellar energy production. But much of it remains in its primordial form, unchanged since the earliest moments of time. When you look up at the night sky, approximately 3/4 of the visible matter you see is hydrogen, ancient primordial hydrogen created in the Big Bang's aftermath. Another quarter is helium from that same era. Everything else, all the carbon, oxygen, nitrogen, iron, and silicon that makes Earth and life possible, represents less than 2% of the cosmic composition. We live in a hydrogen universe, always have, always will. It's the most abundant element in the cosmos by an overwhelming margin, and it's also the simplest. 1 proton, 1 electron. The universe's foundation is simplicity itself. But here's a question that might keep you gently wondering as you drift towards sleep. Why these proportions? Why did the universe settle on making 12 parts hydrogen to 1 part helium? Why not equal amounts? Why not more helium or less? The answer lies in the physics of the early universe. The density, temperature, and expansion rate during those crucial first minutes. Change any of these parameters significantly, and you get a radically different universe. More helium would mean stars would burn differently, potentially too quickly for life to emerge. Less helium might mean not enough raw material for stellar evolution to proceed properly. The recipe we got, this specific mixture of hydrogen and helium with traces of lithium, appears to be, in some deep sense, just right for creating a universe that can develop complexity, form stable stars, build planets, and eventually give rise to life. The primordial ingredients gathered in the cosmic kitchen weren't random. They emerged from physical laws, playing out in the extreme conditions of the early universe, producing proportions that would shape everything that came after. And those ingredients are still here, still abundant, still forming the bulk of cosmic matter. The next time you see a photograph of a nebula, those gorgeous clouds of glowing gas in space, you're looking at primordial material, hydrogen and helium from the Big Bang, mixed with a seasoning of heavier elements from dead stars, ready to collapse and form new stellar generations. The cosmic kitchen is always open, always working with the same base ingredients, always creating new arrangements and possibilities from the simple recipe set down in the first moments of time. But gathering ingredients is only the first step in any recipe. Once you have hydrogen and helium in abundance, you need a way to transform them, to build complexity from simplicity, to create the rich chemical diversity that makes galaxies interesting and life possible. You need a forge where nuclear reactions can occur, where elements can be built up systematically, where the periodic table can begin to fill in. You need, in other words, a star. Deep inside the sun, right now, at this very moment, 600 million tons of hydrogen are being converted into helium every single second. The energy released from this cosmic alchemy is what allows you to see these words, what warms your skin on a summer day, what makes plants grow and ultimately powers nearly all life on Earth. But the sun isn't just producing energy. It's cooking. It's taking the universe's primordial ingredients and slowly, methodically, transforming them into something new. Stars are the universe's first true factories, cosmic forges where nuclear fusion builds elements one step at a time, adding complexity to a cosmos that began with almost none. And the story of how we discovered this might be one of the most beautiful examples of human curiosity leading to cosmic understanding. Let me paint you a picture of the sun's core. It's a place you could never visit, never observe directly, never even point a telescope toward. It's buried beneath 400,000 miles of dense solar material. The temperature there reaches 15 million degrees Celsius. The pressure is 250 billion times Earth's atmospheric pressure at sea level. In these extreme conditions, hydrogen nuclei, protons, are moving so fast and colliding so violently that they overcome their natural electromagnetic repulsion and fuse together. This process, called the proton-proton chain, is remarkably inefficient. A proton in the sun's core might wait, on average, 9 billion years before it successfully fuses with another proton. 9 billion years of bouncing around, colliding millions of times per second, before that one lucky collision that begins the fusion sequence. The sun has been burning for 4.5 billion years, and it still has enough hydrogen fuel for another 5 billion years of steady cooking. But the sun is a gentle chef compared to more massive stars. A star 10 times the sun's mass burns through its hydrogen fuel, not in billions of years, but in millions. A star 30 times solar mass might exhaust its hydrogen in just a few million years. The more massive the star, the hotter its core, the faster its fusion reactions, and the shorter its lifetime. This relationship between stellar mass and lifetime is crucial to understanding cosmic chemistry. It means the universe's element-building processes occur at different rates in different stars, creating a rich temporal tapestry of chemical enrichment. In the 1920s and 1930s, as physicists were just beginning to understand nuclear reactions, a profound mystery troubled astronomers. What powered the stars? What energy source could keep the sun shining steadily for the billions of years that geological evidence suggested Earth had existed? Chemical burning couldn't do it. If the sun were made of coal and oxygen, burning like a giant campfire, it would be consumed in just a few thousand years. Gravitational contraction, the idea that the sun was slowly shrinking and converting gravitational potential energy into heat, could only power the sun for about 20 million years, far too short given evidence of Earth's ancient rocks. The answer came from an unlikely place. A young German physicist named Hans Bethe, who in 1938 attended a conference in Washington, D.C., organized by George Gamow. The conference posed a challenge to physicists: explain the energy source of stars. Bethe took the problem seriously. On the train ride back to Cornell University, he worked through the nuclear physics, calculating reaction rates, energy yields, and temperature requirements. Within weeks, Bethe had worked out 2 different fusion cycles that could power stars. The first, the proton-proton chain, operates in stars like our sun. The second, the CNO cycle, carbon-nitrogen-oxygen cycle, dominates in more massive stars. Both cycles convert hydrogen into helium, releasing tremendous amounts of energy in the process, but they do so through different nuclear pathways. Bethe's papers, published in 1939, earned him the Nobel Prize decades later. But more importantly, they opened the door to understanding how stars could build heavier elements. If fusion could create helium from hydrogen, could it create carbon from helium, oxygen from carbon? Could stars be the cosmic factories that explain the abundance of heavy elements in the universe? The answer is yes, but the process isn't simple or straightforward. It requires understanding how fusion reactions change as a star ages and exhausts different fuels in its core. Let's follow the life story of a massive star, say 15 times the mass of our sun, and watch how it builds elements through successive fusion stages. The star begins its life burning hydrogen in its core, just like the sun, creating a growing core of helium ash. This hydrogen-burning phase lasts for about 10 million years. The star is stable, balanced between the outward pressure of fusion energy and the inward pull of gravity. Eventually, the hydrogen in the core runs out. The star has created a sphere of helium, roughly the size of Earth, but containing several times the mass of our sun. With no fusion reactions to hold it up, the core begins to contract. As it contracts, it heats up. The outer layers of the star, still full of hydrogen, swell outward. The star becomes a red giant, or supergiant. When the contracting helium core reaches about 100 million degrees, something remarkable happens. Helium nuclei begin fusing together. But here's where the process gets interesting and reveals the specific nuclear choreography required for complexity to emerge. A helium nucleus contains 2 protons and 2 neutrons. When 2 helium nuclei collide and fuse, they create beryllium-8, which has 4 protons and 4 neutrons. This sounds promising, but there's a problem. Beryllium-8 is fantastically unstable. It exists for only about 100 million billionth of a second before splitting back into 2 helium nuclei. Under normal circumstances, this would be a dead end. The fusion process could never proceed beyond helium because beryllium-8 falls apart almost instantly. But stars have a secret weapon. They're patient, and they operate at cosmic scales. Even though beryllium-8 is unstable, during its brief existence, there's a tiny probability that another helium nucleus will collide with it before it decays. If this happens, and remember, we're talking about incredibly dense stellar cores where particles are colliding billions of times per second, the beryllium-8 can capture that third helium nucleus and transform into carbon-12. This process is called the triple alpha reaction because it requires 3 helium nuclei, also called alpha particles, to come together in just the right way. And here's where Fred Hoyle's prediction, which we mentioned earlier, becomes absolutely essential. The triple alpha process should be impossibly rare. The probability of 3 helium nuclei coming together in exactly the right configuration before the beryllium-8 decays is astronomically small. Stars should produce almost no carbon, but they do. Carbon is abundant in the universe. We're made of it. How could this be? Hoyle realized that carbon nuclei must have a special energy level, a resonance state, that dramatically increases the probability of the triple alpha reaction succeeding. This resonance acts like a nuclear tuning fork, making the final step of carbon formation much more likely than random chance would suggest. When nuclear physicists tested this prediction in 1957, they found the resonance exactly where Hoyle predicted it would be, at 7.65 million electron volts above carbon's ground state. The universe, it turned out, had a built-in cheat code for creating carbon. Without this precise resonance, carbon would be rare, complex chemistry would be unlikely, and we wouldn't exist to wonder about it. Some scientists and philosophers have pointed to this as evidence of fine-tuning in the universe, that the fundamental constants of nature appear exquisitely calibrated to allow complex chemistry and life. Others view it as a selection effect. We naturally find ourselves in a universe capable of producing observers because we couldn't exist in any other type of universe. Regardless of the interpretation, the fact remains. Stars can manufacture carbon efficiently because of this specific nuclear property. And once carbon exists in stellar cores, further fusion becomes possible. At temperatures around 600 million degrees, carbon nuclei can fuse with helium to create oxygen. The star now has a multi-layered structure, a carbon-oxygen core surrounded by a shell burning helium into carbon, surrounded by another shell burning hydrogen into helium, all wrapped in the star's massive envelope of unburned hydrogen. As the carbon-oxygen core contracts and heats up further, new fusion reactions become possible. At 1 billion degrees, carbon fuses with carbon to create neon, magnesium, and sodium. At 1.5 billion degrees, neon breaks down and fuses to create more oxygen and magnesium. At 2 billion degrees, oxygen fuses with oxygen to create silicon, sulfur, and phosphorus. Each fusion stage produces heavier elements and releases less energy than the previous stage. Hydrogen burning lasts millions of years. Helium burning lasts a few 100,000 years. Carbon burning lasts about 1,000 years. Neon burning lasts 1 year. Oxygen burning lasts mere months. The star is accelerating toward a crisis. Each new fuel source exhausts faster than the last. The energy output per fusion reaction decreases as elements get heavier. The star is running up against fundamental limits of nuclear physics. Finally, at temperatures exceeding 3 billion degrees, silicon burning begins. This process doesn't fuse silicon with silicon in a simple way. Instead, it breaks down silicon nuclei and reassembles them through a complex web of reactions, building progressively heavier elements: sulfur, argon, calcium, titanium, chromium, and ultimately iron. Iron is where the stellar forge reaches its limit. Iron 56 has the highest binding energy per nucleon of any element. This means it's the most stable nuclear configuration possible. Fusing iron into heavier elements doesn't release energy. It requires energy input. The star has finally found a fuel that won't burn. At this point, after perhaps 20 million years of hydrogen burning, followed by increasingly brief episodes of heavier element fusion, the massive star has developed an onion-like structure. At the very center sits an iron core about the size of Earth, but containing more mass than our Sun. This core is surrounded by shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen, each shell representing a different stage of nuclear fusion. The iron core can't generate energy through fusion. With no outward pressure to balance gravity, it begins to collapse. What happens next is spectacular and violent. A supernova explosion that we'll explore in depth shortly. But for now, let's appreciate what the star has accomplished. Starting with just hydrogen and helium, the primordial ingredients from the Big Bang, this stellar forge has systematically built elements up the periodic table: carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, argon, calcium, titanium, chromium, iron. Each element created through precise nuclear reactions, occurring at specific temperatures and densities, each stage building on the products of the previous stage. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was cooked in stellar cores through this step-by-step process. The star that created these elements might have existed billions of years before our Sun formed. It lived, burned through its nuclear fuel, and died, scattering its chemical legacy into space. And here's something that might make you smile. The process is still happening right now, throughout the galaxy, throughout the universe. Stars are still converting hydrogen into helium, helium into carbon, carbon into oxygen. The cosmic recipe is still being executed, billions of years after it began, with no end in sight. Our Sun, modest and middle-aged, will never create elements heavier than carbon and oxygen in tiny amounts. It lacks the mass needed to heat its core enough for advanced fusion stages. When the Sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, fuse helium into carbon and oxygen for a brief period, then gently shed its outer layers and fade as a white dwarf, a dense ember containing the star's chemical legacy. But more massive stars, the heavy element factories of the universe, go through the full sequence, building the periodic table element by element, until they reach iron and can go no further through fusion alone. This raises a fascinating question. If stars can only create elements up to iron through normal fusion, where do all the heavier elements come from? Where was the gold in your jewelry created? The silver in electronics? The uranium in nuclear reactors? What process could forge elements heavier than iron when iron represents the peak of nuclear stability? The answer lies not in the steady burning of stellar cores, but in their catastrophic deaths. When a massive star's iron core collapses, the extreme conditions created in those final moments allow for fusion processes that are impossible during normal stellar life. The cosmic kitchen is about to become a pressure cooker, operating at unimaginable extremes. Every atom of gold that has ever existed, every wedding ring, every ancient treasure, every circuit in every smartphone, was created in approximately 1 second of cosmic violence. Not in the patient burning of stellar cores over millions of years, but in the explosive death throes of massive stars, where temperatures reach billions of degrees and physics operates at its most extreme limits. The universe's most precious elements are born from catastrophe. When a massive star runs out of fuel and its iron core collapses, what follows is one of the most energetic events in the cosmos, a core collapse supernova. In this cosmic pressure cooker, elements heavier than iron, elements that couldn't form through normal fusion, are suddenly forged in abundance. Tonight, we're going to witness the most violent cooking process the universe has ever devised. If these stories of cosmic creation resonate with something deep inside you, if you love exploring how the universe transforms simple ingredients into profound complexity, consider subscribing. Your support helps us continue crafting these journeys through space and time. And a gentle like tells us you'd like more explorations like this one. The story of how we discovered that supernovae create heavy elements is a tale of theoretical brilliance, observational patience, and one spectacular cosmic event that occurred just close enough for us to study in detail. Let's begin with the crisis. A massive star has spent millions of years building an iron core at its center. This iron core, about 1.5 times the mass of our Sun, but compressed into a sphere roughly the size of Earth, can generate no energy through fusion. Iron represents the bottom of the nuclear energy valley. Fusing it into heavier elements requires energy input rather than releasing energy. With no outward pressure from fusion to balance gravity, the iron core begins to collapse. And when I say collapse, I mean something almost incomprehensibly rapid. The core implodes from Earth size to about 20 kilometers across, roughly the size of Manhattan, in less than 1 second. During this collapse, electrons are forced into protons, creating neutrons and releasing ghostly particles called neutrinos. The core becomes so dense that a teaspoon of the material would weigh as much as a mountain on Earth. The temperature spikes to tens of billions of degrees. The infalling material rebounds off this incredibly dense core and generates a shock wave that propagates outward through the star. This shock wave is where the magic happens. As it races through the star's outer layers at speeds of tens of thousands of kilometers per second, it creates conditions even more extreme than those in normal stellar cores. The temperature reaches 5 to 6 billion degrees. The density is enormous, and crucially, there's a flood of neutrons, countless free neutrons released from the collapsing core. In these conditions, atomic nuclei can capture neutrons at an incredible rate. This process, called the R process for rapid neutron capture, can add dozens of neutrons to a nucleus in mere seconds, building up elements far heavier than iron before the nucleus has time to decay. Under normal circumstances, when a nucleus captures a neutron, it becomes slightly heavier and might undergo beta decay, converting a neutron into a proton and moving one step up in atomic number. This slow neutron capture, called the S process, occurs in some stellar environments and creates about half of the elements heavier than iron. But the R process is different. It's violent, rapid, and creates elements that can't form any other way. Neutrons pile onto nuclei faster than decay can occur, creating highly neutron-rich isotopes that then undergo successive beta decays to reach stability. This is how the universe creates elements like gold, platinum, uranium, and thorium. The theoretical foundation for understanding this process was laid in that remarkable 1957 paper by Burbage, Fowler, and Hoyle, the B2FH paper we mentioned earlier. They recognized that two different neutron capture processes must operate in the universe, a slow process occurring in stellar interiors, and a rapid process requiring extreme conditions like those in supernovae. But theory is one thing, observation is another. Scientists needed to catch a supernova in the act, to observe the elements being created in real time, to confirm that these stellar explosions really do forge the heavy elements the theory predicted. On February 23, 1987, a Canadian astronomer named Ian Shelton was working at Las Campanas Observatory in Chile, photographing the Large Magellanic Cloud, a small satellite galaxy of the Milky Way visible from the southern hemisphere. When he developed his photographic plates, he noticed a bright spot that hadn't been there the night before. Shelton was cautious. Bright spots could be artifacts, defects in the plate, problems with the development process. He went outside to check visually, and there it was. A new star blazing in the Large Magellanic Cloud, visible to the naked eye. Supernova 1987A had just announced itself to human observers. This was the closest supernova to Earth observed since 1604, before the invention of the telescope. At a distance of about 168,000 light-years, it was close enough to study in extraordinary detail with modern instruments, but far enough that it posed no danger to Earth. The astronomical community mobilized immediately. Telescopes around the world turned toward SN 1987A. Satellites repositioned to observe it in X-rays and gamma rays. Neutrino detectors, which normally see perhaps a few neutrinos per day, detected bursts of neutrinos from the collapsing stellar core. This was the first direct detection of neutrinos from a supernova, confirming theoretical predictions about core collapse. But what scientists really wanted to see was the emergence of newly created elements. Theory predicted that a supernova should synthesize radioactive isotopes, particularly nickel-56, which decays to cobalt-56, which decays to stable iron-56. This decay chain releases gamma rays with specific identifiable energies. If scientists could detect these gamma rays, it would prove that nuclear fusion was occurring in the supernova, creating new elements exactly as theory predicted. They had to wait. The supernova's outer layers were opaque initially, blocking gamma rays from reaching observers. But as the explosion expanded and thinned, it gradually became transparent. About 4 months after the initial explosion, satellites detected the predicted gamma rays from cobalt-56 decay. The signal was clear, unambiguous, and precisely matched theoretical predictions. The supernova had created new elements exactly as expected. The observations even allowed scientists to calculate how much nickel-56 was produced. About 0.07 solar masses, roughly 70 times the mass of Earth, all created in the moments of stellar death. This was a triumph of theoretical astrophysics. Scientists had predicted decades earlier how supernovae should create elements. When finally given a nearby supernova to study, observations confirmed those predictions in remarkable detail. But SN 1987A taught scientists something unexpected too. The supernova was dimmer than expected and brightened more slowly than standard models predicted. Why? Because the progenitor star, a blue supergiant called Sanduleak 69.2, had a smaller radius than theorists expected for a star about to explode. This forced a revision of supernova models and showed that even well-understood processes can surprise us. Since 1987, astronomers have observed thousands of supernovae in distant galaxies. Each one represents a massive star dying and enriching the cosmos with heavy elements. Each one scatters newly forged atoms into space, where they'll eventually be incorporated into new generations of stars and planets. The gold in jewelry, the platinum in catalytic converters, the uranium in nuclear reactors, all of it came from supernovae. Every gold atom on Earth was created in a supernova explosion somewhere in the galaxy before our solar system formed. Those atoms drifted through space, eventually becoming part of the cloud that collapsed to form the sun and planets. Some found their way into Earth's interior. Geological processes brought them to the crust. Human miners extracted them. Artisans shaped them into objects of beauty. When you hold a gold ring, you're holding matter that experienced temperatures of billions of degrees, pressures beyond human comprehension, and violence that tore apart a star. The ring is quiet now, stable, but it carries within it the memory of cosmic catastrophe. Here's something remarkable about supernovae. They're not just creating heavy elements, they're also solving a cosmic recycling problem. Without supernovae, most of the elements created in stellar cores would remain locked inside white dwarfs and neutron stars, forever removed from the cosmic cycle. Supernovae are the universe's way of distributing the products of stellar nucleosynthesis, ensuring that each generation of stars is slightly richer in heavy elements than the last. The very first stars, forming from primordial gas just a few 100 million years after the Big Bang, contained essentially zero heavy elements, just hydrogen and helium from Big Bang nucleosynthesis. These population 3 stars, as they're called, have never been directly observed because they existed so long ago, but we can infer their existence and properties from theoretical models and from observations of extremely old, metal-poor stars that formed shortly after them. When those first massive stars exploded as supernovae, they enriched their surroundings with the first heavy elements the universe had ever known. The next generation of stars formed from gas that was slightly contaminated with carbon, oxygen, silicon, iron, and traces of heavier elements. Each subsequent generation of stars inherited a richer chemical legacy. Our Sun is a relative latecomer to the cosmic story. It formed about 6 billion years ago from a cloud of gas and dust that had been enriched by countless previous generations of stars. The Sun's composition reflects this heritage. About 73% hydrogen, 25% helium, and 2% heavy elements. That 2% contains the entire periodic table beyond helium: carbon, nitrogen, oxygen, iron, gold, uranium, everything. Earth is made almost entirely from that 2%. We live on the accumulated heavy element debris from ancient stellar explosions. The rocky planets of our solar system, Mercury, Venus, Earth, Mars, represent a tiny fraction of the solar system's mass but contain most of its heavy elements. We're built from cosmic waste products, stellar ash, the debris of long-dead suns. But supernovae might not be the only cosmic ovens capable of creating the heaviest elements. Recent astronomical observations have revealed another process, even more violent than supernovae, that contributes to the universe's heavy element inventory. In August 2017, gravitational wave detectors LIGO and Virgo registered a signal unlike any they had detected before. Instead of the brief chirp from 2 black holes merging, this signal lasted about 100 seconds and showed the characteristic signature of 2 neutron stars spiraling into each other. Within seconds of the gravitational wave detection, telescopes around the world swiveled to the source location. They observed an optical flash followed by a longer-lived infrared glow. The spectrum of this light showed evidence of newly synthesized heavy elements, lanthanides and actinides, the heaviest elements in the periodic table, created through intense R-process nucleosynthesis during the neutron-star merger. This observation confirmed a long-held suspicion. Neutron-star mergers, not just supernovae, contribute significantly to the universe's gold, platinum, and uranium. The colliding neutron stars created a debris field rich in neutrons, providing ideal conditions for rapid neutron capture and heavy element production. Scientists calculated that this single neutron star merger produced about 10 Earth masses of gold, 10 Earth masses, in one event. The gold created in that collision, now dispersing through its host galaxy, will eventually be incorporated into new planetary systems, perhaps ending up in a ring on the finger of some future being, wondering about its cosmic origins. How much gold exists in the universe? It's difficult to estimate precisely, but consider this. A typical galaxy might experience a few supernovae per century, and a neutron star merger every 10,000 years or so. Over billions of years, these events have created and distributed enormous quantities of heavy elements. Yet, gold remains rare. Only about 0.001% of the atoms in the universe are gold. Its scarcity reflects the extreme conditions required for its creation and the relative infrequency of events capable of producing it. This scarcity is why humans value gold, of course. But from a cosmic perspective, gold's scarcity reflects something deeper. The universe's recipes for creating elements heavier than iron require special circumstances. Normal stellar fusion won't suffice. You need catastrophe. Collapsing stellar cores, exploding stars, colliding neutron stars. The universe's most coveted elements are forged only in its most extreme moments. As you breathe slowly and deeply, feeling your body relax into rest, you might reflect on this. The heaviest elements in your body, the tiny traces of elements like zinc, copper, selenium, and iodine that are essential for life, were created in stellar explosions and neutron star collisions. Your body incorporates matter forged in the universe's most violent events, now repurposed for the gentle work of thought, growth, and healing. The cosmic kitchen operates on scales from the patient to the catastrophic, from the gentle fusion in stellar cores over millions of years to the explosive creation of elements in seconds. Both processes are necessary. Both contribute to the rich chemical diversity that makes planets possible, that makes life possible, that makes you possible. But creating the elements is only part of the story. Once supernovae and neutron star mergers have forged these heavy elements and scattered them into space, what happens next? How do these atoms, dispersed by stellar explosions, come together again? How does the universe transform clouds of gas and dust into the next generation of stars and planets? The cosmic recipe continues with a crucial step, the mixing process. Right now, drifting through the space between stars in our galaxy, there are clouds of gas and dust enriched with elements from thousands of ancient supernovae. These clouds are vast, some spanning hundreds of light years across, and they're gradually becoming richer in heavy elements with each passing million years. The universe doesn't just create elements and leave them where they formed. It has developed an elegant recycling system, a cosmic mixing process that ensures the chemical wealth produced in dying stars eventually becomes available to create new worlds, new possibilities, new forms of complexity. The space between stars isn't empty. It's filled with the thin remnants of stellar deaths, the ashes of cosmic fires, waiting patiently to be reborn into something new. Understanding how this mixing happens, how elements spread through galaxies, and how their abundance changes over cosmic time, reveals one of the universe's most patient and beautiful processes. If you're finding peace in these cosmic rhythms, in stories of how the universe slowly transforms and enriches itself, consider joining our community with a subscription. Your like helps more people discover these gentle journeys through space and time. Now, let's watch the cosmos stir its ingredients. The story of cosmic chemical enrichment begins with understanding what happens immediately after a supernova explosion. When a massive star explodes, it doesn't just create new elements. It violently ejects them into surrounding space at speeds of 10 to 20,000 kilometers per second. This expanding shell of stellar debris, called a supernova remnant, carries the star's chemical legacy outward into the interstellar medium. One of the most famous supernova remnants visible to astronomers is the Crab Nebula, located about 6,500 light-years from Earth in the constellation Taurus. This nebula is the expanding debris from a supernova that was observed by Chinese astronomers in the year 1054. They recorded seeing a guest star so bright it was visible during the day for 23 days and remained visible to the naked eye at night for nearly 2 years. Today, nearly 1,000 years later, the Crab Nebula spans about 11 light-years across and is still expanding. Embedded within it is a rapidly spinning neutron star, the collapsed core of the original star, that rotates 30 times per second and powers the nebula's glow. But what's truly remarkable about the Crab Nebula, from our perspective tonight, is its chemical composition. Spectroscopic observations of the Crab Nebula reveal the presence of elements created during the original star's life and explosive death: helium, carbon, oxygen, neon, sulfur, and iron, among others. These elements are thoroughly mixed throughout the nebula, stirred by the turbulent motions of the expanding gas. The supernova didn't just create elements, it homogenized them, blending the products of different fusion stages into a relatively uniform mixture. As the supernova remnant expands, it sweeps up surrounding interstellar gas, mixing the heavy element-rich ejecta with the more pristine hydrogen and helium that fills space. This mixing process is crucial. Without it, the newly created elements would remain concentrated in small regions, unavailable for incorporation into new stars and planets. The expanding remnant eventually slows down as it encounters resistance from the interstellar medium. After tens of thousands of years, it merges with the general interstellar gas, becoming indistinguishable from its surroundings. But its chemical signature remains. The space that supernova enriched now has a slightly higher abundance of heavy elements than it did before. Multiply this process by billions of supernovae over billions of years, and you begin to understand how galaxies gradually increase their heavy element content over cosmic time. Each stellar generation is born from gas that's slightly more enriched than the previous generation. Each supernova adds to the cumulative chemical wealth of its galaxy. In the 1960s and 1970s, astronomers began to observe systematic patterns in stellar chemical compositions that revealed this enrichment history. Beatrice Tinsley, a brilliant New Zealand-born astronomer working at the University of Texas, pioneered the study of galactic chemical evolution. She developed mathematical models showing how galaxies should evolve chemically over time, how their star formation rates, supernova frequencies, and gas dynamics should combine to produce observable patterns in stellar abundances. Tinsley's work faced significant challenges. She was a woman working in a male-dominated field during the 1960s and 1970s. Her marriage struggled under the strain of her career ambitions. Her husband expected her to be a traditional housewife, while she wanted to pursue astronomy professionally. They eventually divorced, and she faced financial hardship while trying to establish herself in academic astronomy. Despite these obstacles, Tinsley produced groundbreaking research. Her 1968 doctoral thesis on galaxy evolution was so advanced that it took years for the astronomical community to fully appreciate its implications. She showed that galaxies aren't static systems, but evolving entities whose colors, brightnesses, and chemical compositions change systematically over billions of years as successive generations of stars form, evolve, and die. Tinsley's models predicted that the oldest stars in a galaxy should have the lowest heavy element abundances, while younger stars should be progressively more enriched. Observations confirmed this prediction beautifully. When astronomers measured the chemical compositions of stars in our galaxy, they found exactly the pattern Tinsley predicted. Old stars have low metallicity. Astronomers call all elements heavier than helium, metals, while younger stars like our Sun have higher metallicity. Our sun's metallicity is about 2%, meaning 2% of its mass consists of elements heavier than helium. This might sound small, but it's actually quite high compared to the oldest stars in our galaxy, some of which have metallicities 1,000 times lower than the sun's. These ancient stars formed from gas clouds that had been enriched by only a few generations of supernovae, while the sun formed from gas enriched by billions of years of stellar processing. Tragically, Beatrice Tinsley died of cancer in 1981 at the age of just 40, cutting short one of the most promising careers in astrophysics. But her legacy lives on in the field she essentially created. Galactic chemical evolution, the study of how galaxies become chemically enriched over time. The mixing process operates on multiple scales simultaneously. On small scales, individual supernova remnants blend their ejecta with surrounding gas over tens of thousands of years. On larger scales, galactic rotation and turbulence stir the interstellar medium, gradually evening out chemical inhomogeneities over millions of years. On the largest scales, interactions between galaxies, mergers and collisions can transport gas across millions of light years, mixing the chemical contents of entire galactic systems. But the mixing isn't perfect or instantaneous. This imperfection creates detectable patterns that tell us about galactic history. For example, the Milky Way galaxy shows a metallicity gradient. Stars near the galactic center tend to have higher heavy element abundances than stars in the outer disk. Why? Because star formation, and therefore supernova rates, has been higher in the dense central regions of the galaxy throughout most of its history. More supernovae mean more chemical enrichment. The outer regions, with lower star formation rates and fewer supernovae, have been enriched more slowly. Astronomers can use these metallicity gradients to reconstruct a galaxy's formation history. A steep gradient might indicate a galaxy that formed quickly, with most of its stars born in an intense burst of star formation. A shallow gradient might suggest a more gradual assembly process, with star formation spreading slowly from the center outward. The Milky Way's chemical evolution story is complex. Studies of stellar ages and compositions suggest the galaxy formed through multiple processes. An initial collapse and burst of star formation about 13 billion years ago, followed by the gradual accretion of smaller satellite galaxies whose stars and gas were incorporated into the main disk. Each infalling satellite brought its own chemical history, its own pattern of enrichment, creating a complex tapestry of metallicities among the galaxy's current stellar population. Some of the oldest stars in the Milky Way, found primarily in the stellar halo surrounding the disk, have extraordinarily low metallicities. These stars formed when the universe was young and had experienced relatively little chemical enrichment. Studying them is like reading an ancient manuscript, learning about the chemical state of the galaxy in its infancy. One particularly interesting group of stars, called R-process enhanced stars, shows unusually high abundances of elements created through rapid neutron capture, the process we discussed occurring in supernovae and neutron star mergers. These stars must have formed from gas clouds that were enriched by a nearby R-process event, probably a neutron star merger, before galactic mixing had time to dilute and homogenize the chemical signature. Think about what this means. The gas cloud that eventually formed that star was enriched by a specific identifiable cosmic event. We can see the chemical fingerprint of an individual neutron star merger preserved in the stellar composition, billions of years after the event occurred. It's like finding a single drop of food coloring before it fully mixes into a glass of water. The inhomogeneity tells us something about the mixing process and its time scale. The mixing process isn't just about spreading elements spatially, it's also about timing. Different elements are produced on different time scales, and this creates temporal patterns in chemical enrichment that astronomers can observe and interpret. Consider iron and oxygen. Both are produced in massive stars, but their production timescales differ. Oxygen is created throughout a massive star's life through helium and carbon burning. When the star explodes as a supernova, the oxygen is immediately released into the interstellar medium. Iron, primarily created during the supernova explosion itself through the decay of radioactive nickel, is also promptly released. But there's another source of iron, type Ia supernovae. These occur when a white dwarf in a binary system accumulates matter from a companion star until it reaches a critical mass and explodes. Type Ia supernovae produce enormous amounts of iron, more than core collapse supernovae, but they occur on longer timescales because it takes time for white dwarfs to accumulate enough mass to explode. The result is a temporal pattern. Early in a galaxy's history, the ratio of oxygen to iron is relatively high because only core collapse supernovae have occurred. Over time, as type Ia supernovae begin exploding, iron abundance increases relative to oxygen. Astronomers can observe this pattern in stellar populations of different ages, reading the galaxy's chemical enrichment history from the changing elemental ratios. These patterns aren't just academically interesting. They constrain our understanding of stellar evolution, supernova physics, and galactic dynamics. By comparing observed elemental abundances with theoretical models, astronomers can test their understanding of how stars produce elements, how often different types of supernovae occur, and how efficiently galaxies mix their chemical contents. Here's a question worth pondering as you rest. How enriched will the universe become? Will galaxies continue producing and mixing heavy elements indefinitely, gradually increasing metallicity towards some asymptotic limit? The answer depends on star formation rates, which in turn depend on gas availability. Galaxies can't form new stars without gas, and various processes remove gas from galaxies. Supernovae blow hot gas out into intergalactic space. Active galactic nuclei powered by supermassive black holes can heat and expel gas, and gravitational interactions between galaxies can strip away gas reservoirs. In our own Milky Way, the current star formation rate is about 1 to 2 solar masses per year, roughly 1 sun's worth of gas converting into stars annually. This might sound substantial, but it's actually quite modest compared to the galaxy's peak star formation rates several billion years ago. The Milky Way is gradually running out of fresh gas to form stars. Its chemical enrichment will continue, but at an ever-slowing pace. Billions of years in the future, star formation in the Milky Way will dwindle as gas supplies are exhausted. The last generation of massive stars will explode as supernovae, adding a final increment to the galaxy's chemical wealth. Then the enrichment process will effectively end. The galaxy will have reached its maximum metallicity, and its chemical composition will change only through the slow evolution of long-lived stars. But we're not there yet. Right now, the Milky Way is still actively mixing and enriching itself. Somewhere in our galaxy at this very moment, a massive star is exploding, scattering newly forged elements into space. Those elements will spread through the interstellar medium, gradually mixing with the ambient gas. In a few million years, that enriched gas might collapse to form a new generation of stars and planets, slightly more metal-rich than the Sun and Earth. This process, explosion, expansion, mixing, collapse, formation, is the fundamental cycle of galactic chemical evolution. It's been operating for billions of years, continuously transforming the simple ingredients from the Big Bang into an ever richer chemical palette. And here's the profound realization. Earth formed at a particular moment in this enrichment history. The Sun and its planets coalesced from a molecular cloud whose composition reflected 9 billion years of chemical enrichment in our galaxy. That specific composition, the particular abundances of carbon, oxygen, silicon, iron, and all the other elements in that cloud, determined what kind of planets could form in the solar system. Had the Sun formed a few billion years earlier, the molecular cloud would have been less enriched. There would have been less carbon, less oxygen, less silicon, less iron. The rocky planets that formed might have been smaller, or compositionally different, or unable to develop the geological complexity that Earth possesses. Had the Sun formed a few billion years later, the cloud would have been more enriched. The planets might have had higher heavy element abundances, different atmospheric compositions, different geological properties. Earth as we know it is a product not just of planetary formation processes, but of the specific moment in galactic chemical evolution when our solar system happened to form. You are, quite literally, a child of your galaxy's chemical enrichment history. The elements in your body were created and mixed over billions of years through countless stellar cycles. The timing of the Sun's formation, determined by the random collapse of a particular molecular cloud at a particular moment, gave you a planet with the right chemical ingredients to support complex geology, liquid water, plate tectonics, and ultimately life. As you breathe slowly, feeling your body settle into rest, you might appreciate this. You're experiencing the latest chapter in a story of chemical transformation that began nearly 14 billion years ago. The mixing process continues, patient and persistent, gradually enriching the cosmos, preparing the raw materials for future worlds that might themselves wonder about their origins. The universe is still cooking, still mixing, still creating new possibilities from ancient ingredients. And from these well-mixed clouds of enriched gas, the next step in the cosmic recipe becomes possible: the formation of planetary systems, where solid worlds can condense from the chemical wealth that generations of stars have provided. 4.5 billion years ago, in an unremarkable region of our galaxy's disk, a cloud of gas and dust began to collapse under its own gravity. This cloud contained all the elements we've discussed: hydrogen and helium from the Big Bang, carbon and oxygen from stellar cores, iron from supernova explosions, traces of gold from neutron star collisions. Within a few million years, this cloud would transform into our solar system: a star, 8 planets, countless moons and asteroids, and one world that would eventually ask how it came to be. The recipe for building rocky planets like Earth requires precise conditions and specific ingredients. Too much of one element, too little of another, and you get a radically different result. Perhaps a gas giant, perhaps a frozen ice world, perhaps no planet at all. Understanding how the right combination of elements came together in the right proportions to build habitable worlds is understanding one of the universe's most elegant construction processes. If these cosmic assembly instructions fascinate you, if you love discovering how simple ingredients combine into profound complexity, your subscription means the world to us. A gentle like helps other curious minds find these stories. Now, let's watch the universe build a world. The process of planet formation begins not with planets, but with dust, microscopic solid particles condensing from cooling gas in a protoplanetary disk. This dust is where the heavy elements we've been discussing finally transition from gas phase to solid form, where chemistry starts creating the minerals that will eventually become rocks, mountains, and continents. The temperature and pressure conditions in different regions of the protoplanetary disk determine which elements condense into solids and when. This creates a natural sorting mechanism. organizing elements by their chemical properties and creating distinct zones where different types of planets can form. Close to the young sun, temperatures were extremely high, over 1,500 Kelvin. At these temperatures, only the most refractory materials, substances with very high condensation temperatures, could exist as solids. These included oxides and silicates of elements like aluminum, calcium, titanium, and magnesium. Most other materials remained in gas phase. The oldest solid objects in the solar system, called calcium aluminum-rich inclusions or CAIs, preserve this high-temperature chemistry. These millimeter-sized inclusions, found embedded in some meteorites, have been precisely dated to 4,507 billion years ago, the very dawn of the solar system. Their composition reflects the chemical conditions in the hottest regions of the early protoplanetary disk. Further from the sun, temperatures were cooler, allowing additional materials to condense. Iron and nickel could form metallic grains. Silicate minerals became more abundant. Beyond a certain distance from the sun, a boundary called the frost line or snow line, temperatures dropped below about 170 Kelvin, cold enough for water ice to form. This boundary, located roughly where the asteroid belt is today, fundamentally divided the solar system into two distinct regions with different planetary outcomes. Inside the frost line, planets would form primarily from rocky and metallic materials, the refractory elements that could condense in the warmer environment. Outside the frost line, planets could incorporate not just rock and metal, but also vast quantities of ice, water ice, methane ice, ammonia ice. These volatile materials are much more abundant in the cosmic mixture than rocky materials, which explains why the outer planets grew so much larger than the inner planets. But before planets could form, dust grains had to grow. And this is where the recipe becomes delicate, because growing from microscopic dust to kilometer-sized planetesimals requires overcoming several significant obstacles. The first challenge is simple sticking. When two dust grains collide gently, they can adhere through molecular forces, van der Waals forces, electrostatic attraction, even ice bridging if water is present. Laboratory experiments show that fluffy dust aggregates can grow this way up to about a centimeter in size. But beyond a centimeter, the mechanism breaks down. Larger objects collide with more energy. And instead of sticking together, they tend to bounce off each other, or even fragment. This is called the bouncing barrier, and for decades it puzzled planetary scientists. How did the solar system get past this stage? The answer involves several mechanisms working together. Turbulence in the protoplanetary disk can concentrate dust into localized regions, where densities are high enough for gravitational collapse to directly form kilometer-sized bodies. Sticky ice coatings beyond the frost line help aggregates hold together during more energetic collisions. And certain minerals, when they collide, can fracture in ways that create fresh, sticky surfaces that promote growth rather than fragmentation. Once objects reach kilometer sizes, now called planetesimals, gravitational attraction becomes significant. These planetesimals begin to preferentially accrete smaller objects in their vicinity. The rich get richer. Larger planetesimals grow faster than smaller ones, eventually dominating their orbital zones and growing into planetary embryos. The story of how scientists discovered these formation processes is filled with patient observation, clever experimentation, and occasional lucky breaks. In the 1970s, Soviet scientist Viktor Safronov developed the mathematical framework for understanding planetesimal accretion. Working largely in isolation from Western scientists during the Cold War, Safronov calculated how gravitational focusing, the enhancement of collision cross-sections due to gravity, would allow planetesimals to grow efficiently. Safronov's work laid the foundation for modern planet formation theory, but it remained largely unknown outside the Soviet Union until it was translated into English in 1972. When Western scientists finally read Safronov's monograph, they realized he had solved many of the problems they had been struggling with independently. Building on Safronov's work, scientists in the 1980s and 1990s developed increasingly sophisticated computer simulations of planet formation. These simulations revealed a chaotic, violent process. Planetesimals don't gently accrete into planets. They collide, shatter, merge, scatter each other through gravitational interactions, and undergo catastrophic impacts that can melt or even vaporize them. Earth itself bears evidence of this violence. The Moon, our planet's largest satellite, is thought to have formed from debris ejected when a Mars-sized object called Theia collided with the proto-Earth about 4.5 billion years ago. This giant impact melted Earth's surface, vaporized parts of both colliding bodies, and ejected enough material into orbit to coalesce into the Moon. The impact was so energetic that it likely homogenized Earth's composition, mixing the core and mantle materials and creating the chemically distinct layers we observe today only after the planet cooled and differentiated. Evidence for the giant impact hypothesis comes from multiple sources. Moon rocks returned by Apollo missions have the same oxygen isotope ratios as Earth rocks, suggesting they formed from the same source material. The Moon has a very small iron core compared to Earth, consistent with it forming primarily from mantle material ejected in the collision. And computer simulations show that impacts of the required magnitude naturally produce a disk of debris that matches the Moon's mass and orbital properties. But here's what's remarkable. Despite this violence, despite the chaos and catastrophe of planet formation, Earth ended up with a remarkably fortuitous composition. The mixture of elements in our planet, the silicon and oxygen forming silicate minerals, the iron and nickel comprising the core, the water creating oceans, the carbon enabling organic chemistry, represents a Goldilocks combination. Let's examine Earth's elemental recipe more closely. By mass, Earth consists of approximately 32% iron, 30% oxygen, 15% silicon, 14% magnesium, with the remaining 9% distributed among dozens of other elements. This composition reflects the initial mixture of dust in the inner solar system, modified by processes like differentiation, volatile loss, and late accretion. The iron, being dense and somewhat immiscible with silicates, sank to Earth's center during the planet's molten phase, forming the metallic core. This core comprises about 1/3 of Earth's mass, but only 1/6 of its volume because iron is much denser than rock. The core's existence has profound implications. Its slow convection generates Earth's magnetic field, which shields the surface from harmful solar radiation and prevents the solar wind from stripping away the atmosphere. Without iron in the right abundance, without those supernova explosions that created iron atoms, without the giant impact that helped Earth differentiate into core and mantle, Earth might have no magnetic field. Without a magnetic field, the atmosphere would gradually erode, water would be lost to space, and the surface would be bathed in radiation, hostile to complex life. The silicon and oxygen, forming silicate minerals, constitute Earth's mantle and crust. These light elements float atop the iron core, creating the rocky surface we inhabit. The specific silicate minerals that form depend on temperature, pressure, and the availability of other elements. Magnesium-rich olivine dominates the upper mantle. Pyroxenes, feldspars, and quartz are abundant in the crust. Each mineral represents a specific elemental recipe, a particular combination of atoms arranged in a crystalline structure. Earth's water, comprising the oceans, ice caps, groundwater, and atmospheric water vapor, amounts to only about 0.02% of the planet's mass. Yet this tiny fraction is crucial. Water is an excellent solvent, enabling the chemical reactions that make life possible. It moderates temperature through its high heat capacity. Its unique property of expanding when freezing means ice floats, preventing oceans from freezing solid from the bottom up. Where did Earth's water come from? This question has puzzled scientists for decades. Water is a volatile compound that should have been vaporized or driven away from the inner solar system by the young sun's heat. Yet Earth clearly has substantial water. How did it get here? The answer involves late-stage delivery from the outer solar system. After the terrestrial planets largely formed, they continued to be bombarded by asteroids and comets for hundreds of millions of years, an era called the Late Heavy Bombardment. Many of these impactors came from beyond the frost line and carried significant amounts of water ice. When they crashed into Earth, they delivered their water cargo, gradually building up Earth's oceans. Evidence for this delivery mechanism comes from isotope ratios. Water molecules contain hydrogen, which comes in two stable isotopes: ordinary hydrogen with one proton, and deuterium with one proton and one neutron. The ratio of deuterium to hydrogen in Earth's oceans matches certain types of asteroids from the outer asteroid belt better than it matches most comets, suggesting asteroids were the primary water delivery vehicles. But not all rocky planets are created equal, even within our own solar system. Comparing Earth to its neighbors reveals how subtle differences in composition and formation history produce radically different worlds. Venus, Earth's near twin in size and mass, formed closer to the Sun, where temperatures were slightly higher. This seemingly minor difference had profound consequences. Venus's proximity to the Sun meant any water on its surface would evaporate more readily. Water vapor, a potent greenhouse gas, trapped heat and triggered a runaway greenhouse effect. Surface temperatures soared to over 450 degrees Celsius, hot enough to melt lead. Any remaining water was broken down by ultraviolet light and lost to space. Today, Venus is a hellish desert world with a crushing carbon dioxide atmosphere, despite having nearly identical bulk composition to Earth. Mars, forming farther from the Sun, where less material was available, ended up smaller, only about 11% of Earth's mass. This had cascading consequences. Mars cooled faster, its core solidified earlier, and its magnetic field shut down relatively quickly. Without a magnetic field, the solar wind gradually stripped away much of Mars's atmosphere. Surface pressure dropped, liquid water became unstable and either froze or evaporated, and the planet transformed into the cold, dry desert we observe today. Mercury, closest to the Sun, experienced even more extreme conditions. The intense solar radiation and proximity to the Sun's gravity well meant that lighter elements were preferentially lost. Mercury ended up with an unusually large iron core, about 60% of its mass, and a thin silicate mantle. It's essentially a giant iron ball with a rocky coating, representing the most extreme composition of any planet in our solar system. These comparisons teach us something profound. The recipe for a habitable world like Earth requires not just the right elements in the right proportions, but also the right formation location, the right sequence of events, and considerable luck. Earth's habitability is not just about its composition, it's about its mass, its distance from the Sun, its retention of water, the preservation of its magnetic field, the stabilizing influence of the Moon, and dozens of other factors that had to align favorably. Scientists sometimes call this the Goldilocks principle. Earth is not too hot like Venus, not too cold like Mars, not too small to hold an atmosphere, not so large that it captured a thick hydrogen envelope like the gas giants. Everything is, as the fairy tale says, just right. But we should be careful not to overstate this. Earth isn't uniquely or mysteriously perfect. Rather, Earth is one outcome from a very large number of planetary formation experiments the universe has conducted. In our galaxy alone, there are hundreds of billions of stars, many with their own planetary systems. The sheer number of attempts means that many Earth-like worlds likely exist, each the product of a favorable combination of circumstances in their own formation histories. Since 1995, when the first exoplanet orbiting a sun-like star was discovered, astronomers have detected thousands of planets around other stars. These exoplanets show astonishing diversity. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths with masses between Earth and Neptune. Water worlds covered entirely in deep oceans, and rocky planets orbiting tiny red dwarf stars. This diversity reveals that planet formation is not a deterministic process with a single outcome, but a stochastic process with many possible outcomes depending on initial conditions and random events. The recipe for building planets has many variations, and each produces something different. What makes Earth special isn't that it's the only possible outcome, but that it represents one particularly interesting outcome: a mid-sized rocky planet with liquid water, a protective magnetic field, and just the right elemental composition to support complex geology and, eventually, biology. As you settle into rest, breathing slowly and deeply, consider this: the ground beneath you, the air you breathe, the water in your cells, all of it came together through a series of physical processes that transformed dust into a world. Gravity pulled particles together, collisions built larger bodies, differentiation sorted elements by density, late bombardment delivered water. And from these mechanical chemical processes, operating according to simple physical laws, Earth emerged. The planet you inhabit is made from the same stardust that fills the cosmos, organized through planetary formation into a unique configuration that can support oceans, continents, weather, seasons, and life. You live on a world whose every atom has a history, whose overall composition reflects billions of years of cosmic chemical evolution, and whose specific arrangement of those atoms created the conditions that made your existence possible. But having the right chemical ingredients for life is not the same as having life. A kitchen stocked with flour, eggs, sugar, and butter is not the same as a cake. Something must act upon the ingredients, must combine them in the right ways, must transform potential into actuality. For life to emerge, the universe needed not just the right elements and the right planet, but the right chemistry. Of all the elements in the periodic table, 94 occurring naturally, life on Earth uses only about 25 regularly, and relies absolutely on just 6: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements, sometimes abbreviated as CHNOPS, form the backbone of every living thing on this planet. But what makes these particular elements so special? Why did life choose carbon as its structural foundation rather than silicon? Why is water essential rather than methane or ammonia? The recipe for life is written in chemistry, and understanding why certain ingredients are irreplaceable reveals one of the universe's most elegant solutions to the problem of complexity. Life isn't just chemistry, but it begins with chemistry, with the unique properties of certain atoms and molecules that make self-organization, replication, and evolution possible. The story of how scientists discovered which elements life requires and why these elements work so perfectly together is a journey through the very foundations of biochemistry. If you're finding wonder in how the universe built not just planets, but living things from cosmic ingredients, your subscription and help us share these discoveries with more dreamers like you. Now, let's explore the chemistry of being alive. Let's start with carbon, the element that makes you possible. Carbon sits in the middle of the periodic table's second row, with 6 protons, 6 neutrons, and 6 electrons. This position gives carbon a unique chemical superpower. It can form 4 strong covalent bonds with other atoms, including with other carbon atoms. This might sound technical, but the implications are profound. Carbon's 4-bond capacity means it can create chains, branches, rings, and 3-dimensional structures of essentially unlimited complexity. A single carbon atom can bond to 4 other carbons, each of which can bond to 4 more, and so on, creating molecular architectures of astonishing intricacy. No other element offers this flexibility. Silicon, directly below carbon in the periodic table, also forms 4 bonds and is far more abundant in Earth's crust than carbon. Science fiction writers have long speculated about silicon-based life, but silicon has crucial limitations that carbon doesn't. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains unstable. Silicon dioxide, the product of silicon burning with oxygen, is a solid at room temperature, unlike carbon dioxide, which is a gas. A silicon-based organism would effectively turn to stone when it respired. The discovery of carbon's central role in life began in the early 1800s, when chemists started to distinguish between compounds derived from living things and those from minerals. Friedrich Wöhler's synthesis of urea from inorganic compounds in 1828 shocked the scientific world. It proved that organic molecules weren't fundamentally different from inorganic ones, that they could be created through ordinary chemistry without a mysterious, vital force. This opened the door to understanding life as chemistry. By the late 1800s, chemists recognized that carbon was the common thread linking all organic compounds. But understanding why carbon was so essential required developing quantum mechanics and molecular orbital theory in the 20th century, which revealed the unique bonding properties that make carbon-based chemistry so versatile. The second essential element for life is hydrogen, the simplest and most abundant element in the universe. Hydrogen forms the backbone of organic molecules alongside carbon. Every organic compound contains carbon-hydrogen bonds. But hydrogen's role goes far beyond structural support. Hydrogen bonding, a weak attractive force between hydrogen atoms and electronegative atoms like oxygen and nitrogen, is absolutely crucial for life. This interaction is what makes water such an extraordinary solvent, what holds the 2 strands of DNA together in their famous double helix, what gives proteins their 3-dimensional shapes, what allows cells to maintain their internal organization. Without hydrogen bonding, life as we know it couldn't exist. Water itself, H2O, 2 hydrogen atoms bonded to 1 oxygen, deserves special attention, because its properties are so perfectly suited for life that they seem almost designed for the purpose. Water is an exceptional solvent, capable of dissolving more substances than any other common liquid. This allows it to transport nutrients, remove waste products, and provide a medium where biochemical reactions can occur. Water has an unusually high heat capacity, meaning it takes a lot of energy to change its temperature. This makes water an excellent temperature buffer, protecting living systems from rapid temperature fluctuations. Earth's oceans store vast amounts of heat, moderating global climate. Your body uses water to maintain a stable internal temperature despite changing environmental conditions. Water's density maximum at 4 degrees Celsius, meaning ice is less dense than liquid water, has profound implications. Ice floats. This prevents bodies of water from freezing solid from the bottom up, allowing aquatic life to survive winters. If ice sank, Earth's oceans might have frozen solid early in their history, potentially preventing life from ever emerging. The Russian biochemist Alexander Oparin was one of the first scientists to seriously investigate how life might have originated from non-living chemistry. In the 1920s, working in the Soviet Union, Oparin proposed that Earth's early atmosphere might have been chemically reducing, rich in hydrogen, methane, and ammonia, and that energy from lightning or ultraviolet radiation could have driven chemical reactions that created simple organic compounds. Oparin's ideas remained largely theoretical until 1952, when American graduate student Stanley Miller, working with his advisor Harold Urey at the University of Chicago, decided to test them experimentally. Miller created a sealed glass apparatus containing water, methane, ammonia, and hydrogen, gases thought to represent Earth's early atmosphere. He subjected this mixture to electrical sparks, simulating lightning for a week. The results were stunning. After just 7 days, the water in Miller's apparatus had turned murky and brown. Chemical analysis revealed that it contained several amino acids, the building blocks of proteins. Miller had created organic compounds, including components of life, from simple inorganic starting materials. The Miller-Urey experiment, as it became known, revolutionized origin of life research. It demonstrated that the gap between non-living chemistry and the chemistry of life wasn't as vast as many had assumed. Given the right conditions and raw materials, complex organic molecules could form spontaneously. However, later research suggested that Earth's early atmosphere was probably not as reducing as Miller and Urey assumed. It likely contained more carbon dioxide and nitrogen, with less methane and ammonia. When the experiment is repeated with these more realistic atmospheric compositions, amino acid production is less efficient, though it still occurs. This brings us to nitrogen, the third essential element. Nitrogen makes up about 3% of your body weight and is a crucial component of amino acids, proteins, and nucleic acids like DNA and RNA. Despite nitrogen gas comprising 78% of Earth's atmosphere, most organisms cannot use atmospheric nitrogen directly. The triple bond holding N2 molecules together is extraordinarily strong, among the strongest chemical bonds known. Life solved this problem through nitrogen fixation, the process of breaking apart N2 molecules and incorporating nitrogen atoms into organic compounds. Certain bacteria evolved the ability to fix nitrogen using specialized enzymes called nitrogenases. These enzymes are so complex and energy intensive that cells must invest enormous resources to maintain them. Yet nitrogen fixation is so essential that it has evolved multiple times independently. Without nitrogen-fixing bacteria, the biological world would look radically different. Most nitrogen in organisms comes ultimately from bacterial nitrogen fixation. Plants obtain nitrogen from soil bacteria. Animals obtain it by eating plants or other animals, and when organisms die, decomposers return nitrogen to the soil where it can be fixed again. This nitrogen cycle is one of Earth's fundamental biogeochemical cycles. Oxygen, despite being essential for most complex life today, was actually poisonous to Earth's earliest organisms. The early Earth had an atmosphere with very little free oxygen. The first life forms were anaerobic, thriving without oxygen and often being harmed by it. Everything changed around 2.4 billion years ago, when cyanobacteria, photosynthetic microorganisms, evolved the ability to split water molecules and use the hydrogen to fix carbon dioxide, releasing oxygen as a waste product. This oxygen accumulated in the atmosphere over hundreds of millions of years, eventually reaching modern levels around 21%. This event, called the Great Oxidation Event, was catastrophic for anaerobic life. Oxygen is highly reactive and damages cellular components. Many species went extinct, but the crisis created opportunity. Oxygen allows for aerobic respiration, which extracts far more energy from food molecules than anaerobic metabolism. Complex multicellular life, with its high energy demands, became possible only after oxygen levels rose. Today, most organisms use oxygen for respiration, taking advantage of its reactivity to extract energy from nutrients. The very property that made oxygen poisonous to early life, its tendency to grab electrons from other molecules, makes it perfect for the final step in cellular respiration, where it acts as the ultimate electron acceptor in the process that generates ATP, the cell's energy currency. Phosphorus, though present in organisms at only about 1% by weight, plays roles utterly disproportionate to its abundance. Phosphorus forms the backbone of DNA and RNA molecules, linking nucleotides together in the famous double helix. It's the P in ATP, adenosine triphosphate, the molecule that stores and transfers energy in cells. Phosphorus is a key component of cell membranes, which are built from phospholipids. Unlike carbon, nitrogen, and oxygen, phosphorus has no gaseous phase under normal Earth conditions. This means there's no atmospheric reservoir of phosphorus. Organisms must obtain phosphorus from rocks, where it's slowly released through weathering or from other organisms. Phosphorus scarcity often limits biological productivity in ecosystems. Add phosphorus to a pond and algae bloom. Remove phosphorus and growth slows. The astronomer and astrobiologist Carl Sagan once speculated that life might exist based on other chemistries in radically different environments. Perhaps ammonia-based life in cold moons, or life using liquid methane as a solvent on Saturn's moon Titan. While such exotic biochemistries are theoretically possible, carbon water-based life has such overwhelming advantages that it's likely the most common form of life in the universe, if life exists elsewhere. Sulfur, the sixth of the essential elements, rounds out the Schnapps recipe. Sulfur forms crucial bonds in proteins, creating bridges between protein chains that give them their three-dimensional shapes. Some amino acids contain sulfur. Many enzymes require sulfur-containing cofactors to function. Certain microorganisms can even use sulfur compounds in their metabolism, filling the role that oxygen plays in aerobic organisms. Beyond these 6 major elements, life requires traces of many others. Iron is essential for hemoglobin, which transports oxygen in blood. Magnesium sits at the heart of chlorophyll, enabling photosynthesis. Calcium provides structure to bones and teeth and acts as a signaling molecule in cells. Zinc, copper, manganese, molybdenum, cobalt. Each plays specific, irreplaceable roles in various enzymes and biological processes. What's remarkable is how life has learned to use almost every available element, finding roles for atoms that are rare and selecting them from the environment with extraordinary precision. Your body contains gold atoms, platinum atoms, even radioactive uranium atoms at trace levels. While these aren't essential, their presence demonstrates how thoroughly life samples the periodic table. The relative abundances of elements in living things don't perfectly match their abundances in Earth's crust or oceans. Life has preferences, selecting certain elements over others. This selectivity reveals something profound. Life isn't just passive chemistry, but active chemistry that reaches out into the environment and pulls in the atoms it needs while excluding others. Think about sodium and potassium. These 2 elements are chemically similar. Both are alkali metals in the same column of the periodic table. In seawater, sodium is far more abundant than potassium, yet cells maintain internal potassium concentrations far higher than external sodium concentrations. They actively pump sodium out and potassium in, using energy to maintain this imbalance. Why? The answer involves subtle differences in how these ions interact with biological molecules. Potassium is slightly larger than sodium and has a lower charge density. These properties make potassium better suited for certain biological roles, particularly in nerve signaling and protein function. Life discovered this difference early in its history and designed cellular machinery to exploit it. This brings us to a profound realization. The recipe for life isn't just about having the right elements present. It's about having them in the right proportions, in the right forms, in the right places, at the right times. A cell isn't just a bag of chemicals. It's an exquisitely organized system that maintains concentrations and distributions far from chemical equilibrium. Creating this organization requires energy. Life is constantly working against entropy, building ordered structures from disordered raw materials, maintaining concentration gradients, repairing damage, and preventing decay. This is why all life forms need an energy source: sunlight for photosynthetic organisms, chemical energy for everything else. The Austrian physicist Erwin Schrödinger, who made foundational contributions to quantum mechanics, wrote a small book in 1944 called What is Life?, in which he grappled with this question from a physicist's perspective. Schrödinger recognized that living systems appear to violate the second law of thermodynamics, which states that entropy, disorder, must increase over time. Living things are highly ordered and become more ordered as they grow and develop. Schrödinger's answer was that living things avoid entropy increase by feeding on negative entropy from their environment. They consume ordered energy, food, sunlight, and export disorder in the form of heat and waste products. Locally, in the organism itself, entropy decreases and order increases, but the total entropy of the universe still increases when you account for all the disorder the organism creates in its surroundings. This perspective reframes life as a thermodynamic phenomenon, a particular way that matter and energy can organize themselves under far from equilibrium conditions. Life doesn't violate physical laws. It exploits them, finding ways to create local order by increasing global disorder. As you rest, breathing slowly and rhythmically, you might appreciate this. Every breath you take brings in oxygen atoms forged in dying stars. Every heartbeat circulates iron atoms created in supernova explosions. Every thought arises from patterns of carbon, nitrogen, and phosphorus atoms arranged in extraordinarily specific ways. You are chemistry in action, matter organized in a pattern that can think, feel, remember, and wonder. The recipe for life required not just any elements, but specific elements with specific properties. Carbon for structural complexity, hydrogen for bonding versatility, nitrogen for the diversity of proteins and nucleic acids, oxygen for efficient energy extraction, phosphorus for information storage and energy transfer, sulfur for protein structure, plus traces of dozens of others for specialized functions. These elements had to come together in just the right combinations, in just the right environment. Liquid water at moderate temperatures, a stable energy source, protection from harmful radiation, time for chemistry to experiment and complexify. Earth provided these conditions, and life emerged. But here's the deepest mystery. Life isn't just made from these elements. Life is these elements, organized in ways that can maintain their own organization, that can replicate, that can evolve. The recipe for life doesn't just describe what ingredients you need. It describes a process, a dance of chemistry that perpetuates itself and becomes, in a sense, more than the sum of its chemical parts. You exist at the culmination of this process, billions of years of chemistry learning to organize itself more intricately, more adaptively, more exquisitely. The atoms in your body aren't special atoms. They're ordinary atoms, forged in cosmic processes we've explored throughout this journey. What makes them special is their current arrangement, the specific pattern they form that is you. Every 7 years, most of the atoms in your body are replaced. The carbon in your skin, the calcium in your bones, the iron in your blood, all gradually recycled, exhaled as carbon dioxide, excreted as waste, shed as dead cells, and replaced with new atoms from the food you eat, the water you drink, the air you breathe. You are not a static collection of matter, but a dynamic pattern, a temporary arrangement of atoms borrowed from the universe, held together briefly in the form of you, then returned to the cosmic cycle. You are a verb, not a noun, a process, not a thing. Understanding what you're made of, tracing each element in your body back to its cosmic origin, reveals the most profound connection between human existence and the universe's 13 billion year story. You are not just in the universe, you are the universe, localized, aware, contemplating itself. If this perspective brings you peace, if these connections between cosmic processes and your own existence resonate with something deep inside, your subscription helps us continue exploring these profound truths. A gentle like helps others discover their place in the cosmos. Now, let's trace your atomic ancestry. Let's begin with the most abundant element in your body, oxygen. About 65% of your body mass is oxygen, most of it bound in water molecules. Every oxygen atom you contain was created inside a massive star that lived billions of years ago, probably dozens of times more massive than our sun. That star spent millions of years in its helium-burning phase, fusing helium nuclei together through the triple alpha process to create carbon. Then, as its core heated further, carbon nuclei fused with helium to create oxygen. This oxygen accumulated in the star's core and surrounding shells, waiting. When the star finally exploded as a supernova, perhaps 5 billion years ago or even earlier, it scattered its oxygen into interstellar space. Those oxygen atoms drifted through the galaxy, became part of a molecular cloud, collapsed with that cloud to form the solar system, incorporated themselves into Earth's minerals and water, cycled through geological processes, entered the atmosphere, and eventually, just recently in cosmic time, became part of you. The oxygen atoms in your lungs right now have made this extraordinary journey. They've been parts of countless organisms before you, dinosaurs, trees, bacteria, perhaps even early humans. They've been ocean water, polar ice, desert sand, volcanic gas, and now, temporarily, they're you. With every breath, you're exchanging oxygen atoms with the world around you, participating in an atomic cycle that connects you to every breathing thing that's ever lived. Carbon makes up about 18% of your body mass. While less abundant than oxygen, carbon is in some ways more interesting because of its versatility. Carbon forms the backbone of every organic molecule in your body. Your DNA, your proteins, your fats, your carbohydrates. You are fundamentally a carbon-based life form. The carbon in your body was also forged in stellar cores, created when helium nuclei came together in that remarkable triple alpha process that Fred Hoyle predicted. But carbon has a more diverse history than oxygen because it cycles through Earth's systems in different ways. Some carbon in your body was recently absorbed by plants from atmospheric carbon dioxide during photosynthesis. Those plants broke apart CO2 molecules, kept the carbon to build their tissues, and released the oxygen. You ate those plants, or ate animals that ate those plants, and incorporated that carbon into your own structure. But where did that atmospheric carbon dioxide come from? Some was released by respiring organisms, animals breathing out. bacteria decomposing organic matter. Some came from volcanic eruptions, bringing carbon from deep in Earth's interior to the surface. Some was released from burning fossil fuels, ancient plants and animals whose carbon was locked in coal and oil for hundreds of millions of years before humans extracted and burned them. Trace any carbon atom in your body back far enough, though, and you reach the same origin. Fusion reactions in the core of a red giant star, probably between 5 and 8 billion years ago, before our solar system existed. Hydrogen accounts for about 10% of your body by mass, though by number of atoms, hydrogen is actually the most abundant element in your body because hydrogen atoms are so light. Most of your hydrogen is bound in water molecules and inorganic compounds. The hydrogen in your body is special because it's primordial. Unlike carbon and oxygen, which were cooked in stars, the hydrogen atoms in your body were created in the first 3 minutes after the Big Bang. These atoms have existed for 13.8 billion years, making them the oldest parts of you by far. Think about that for a moment. The hydrogen in your cells, in your DNA, in the water that makes up most of your body. Those atoms are nearly as old as the universe itself. They've witnessed cosmic history. They were there when the first stars ignited. They were there when galaxies formed. They've cycled through perhaps thousands of stars and countless planets before ending up, temporarily, as part of you. Nitrogen, comprising about 3% of your body mass, is essential for proteins and DNA. The nitrogen in your body was created in massive stars through the CNO cycle, carbon-nitrogen-oxygen cycle, which is one of the fusion processes that powers stars more massive than the Sun. In this cycle, carbon, nitrogen, and oxygen act as catalysts, facilitating the fusion of hydrogen into helium while being recycled themselves. Some nitrogen is created as a byproduct. When the massive star eventually exploded, it scattered this nitrogen into space, where it eventually found its way into Earth's atmosphere. Most nitrogen enters your body through your diet. Plants absorb nitrogen from soil, where bacteria have fixed atmospheric nitrogen into usable forms. You eat plants or plant-eating animals, and their nitrogen becomes your nitrogen, incorporated into your amino acids, your proteins, your nucleotides, your DNA. Every amino acid and every protein in your body contains nitrogen from dead stars. When you build muscle, grow hair, replace skin cells, or create enzymes, you're using nitrogen that was forged in stellar nuclear reactions billions of years ago and has been cycling through Earth's biosphere for eons. Calcium comprises about 1.5% of your body mass, mostly in your bones and teeth. Calcium gives your skeleton its strength and rigidity, but calcium atoms also play crucial signaling roles in cells, triggering muscle contractions, neurotransmitter releases, and countless other cellular processes. Calcium was created through silicon burning in the final moments of massive star evolution, just before the star's core collapsed and triggered a supernova explosion. The extreme temperatures, over 3 billion degrees, allowed silicon to fuse into heavier elements, including calcium. When you feel your bones, when you move your muscles, when neurons fire in your brain, you're using calcium that experienced some of the most extreme conditions in the universe. These atoms were forged in temperatures that would vaporize anything we're familiar with, in environments where the laws of physics operate at their limits. Now, those same atoms provide structure to your skeleton and enable your nervous system to function. Phosphorus, about 1% of your body mass, forms the backbone of DNA molecules and is the key component of ATP, the energy currency of cells. Phosphorus was also created in supernova explosions through a process called explosive oxygen burning, which occurs in the outer layers of an exploding star as the supernova shockwave passes through. The phosphorus in your DNA, the very molecules that carry your genetic information, that make you uniquely you, was forged in stellar catastrophe. The double helix structure of DNA is held together by a sugar-phosphate backbone, and every phosphorus atom in that backbone was created in a dying star's final moments. Your genetic code, the instructions for building you, is literally written in stardust. The medium is the message. You exist because stars died, because they scattered their chemical wealth into space, because that enriched material eventually became part of Earth, and because the right combinations of elements assembled themselves into patterns capable of storing and transmitting information. Iron in your blood, about 0.06% of your body mass, but absolutely essential, is perhaps the most poignant example of cosmic recycling. Iron cannot be created through normal fusion in stars because it's at the peak of nuclear binding energy. The iron in your hemoglobin was created either in the final moments of silicon burning before a star went supernova, or possibly during the supernova explosion itself. Right now, your blood contains about 3 to 4 grams of iron, distributed among roughly 25 trillion red blood cells. Each red blood cell contains about 270 million hemoglobin molecules. Each hemoglobin molecule contains 4 iron atoms. That's over 2 billion iron atoms in your blood, all of them forged in stellar deaths. These iron atoms bind oxygen in your lungs and release it in your tissues, enabling aerobic respiration. Without iron, without this element that stars can't create through ordinary fusion, complex life would be impossible. Your consciousness, your thoughts, your ability to contemplate these words all depend on iron atoms delivering oxygen to your brain cells. The human body also contains traces of dozens of other elements, each with its own cosmic origin story. The zinc in enzymes, the copper in connective tissues, the selenium in antioxidants, the iodine in thyroid hormones, the cobalt in vitamin B12. All were created in various stellar processes and nucleosynthetic pathways. Some elements in your body are radioactive, albeit at very low levels. Potassium-40, a naturally occurring radioactive isotope, exists in your body at about 20 milligrams. It slowly decays, emitting radiation inside you. You are literally very slightly radioactive. This radioactivity comes from supernova explosions. The same processes that created stable elements also created unstable ones that are still slowly decaying billions of years later. In 1980, Carl Sagan brought these ideas to mainstream consciousness through his television series Cosmos, in which he famously said, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." This phrase, "we are made of star stuff," resonated profoundly with people around the world. It captured something essential about our relationship to the cosmos. We're not separate from the universe, not observers standing outside looking in. We are the universe observing itself, matter organized in a form capable of contemplating its own origins. But Sagan's beautiful phrase, while true, doesn't fully capture the process. You're not just made of star stuff, you're made of recycled star stuff. The atoms in your body have been through multiple cycles of stellar birth and death. They've been parts of earlier planetary systems that formed, existed, and were destroyed. They've cycled through Earth's geology and biosphere countless times. The average age of atoms in your body is difficult to calculate precisely, but we can make some estimates. Hydrogen atoms, 13.8 billion years old from the Big Bang. Carbon, nitrogen, oxygen atoms, probably 5 to 10 billion years old from stars that lived and died before the solar system formed. Some atoms might be younger, from stars that exploded more recently and whose ejecta happened to end up in the molecular cloud that formed our solar system. Your atoms are older than Earth. They're older than the sun. Some are nearly as old as the universe itself. You are, quite literally, ancient. Every atom in your body has existed far longer than you have, and will exist far longer than you will. You're a temporary custodian of these atoms, borrowing them briefly before returning them to the cosmic cycle. This perspective can be simultaneously humbling and empowering. Humbling because you're not separate from nature, not made of special materials, not exempt from physical laws. Your atoms are ordinary atoms that happen to be arranged in an extraordinary pattern. When you die, those atoms will be released and recycled, eventually becoming parts of other organisms, other geological formations, perhaps eventually other solar systems and stars. But the perspective is also empowering because it connects you to the largest story there is. You're not just the product of your parents, your culture, your historical moment. You're the product of cosmic evolution, of the Big Bang, of stellar nucleosynthesis, of galactic chemical enrichment, of planetary formation, of biological evolution. The lineage of your atoms stretches back to the beginning of time. Some traditions and philosophies have long taught that humans are fundamentally connected to nature, to the earth, to the cosmos. Modern astrophysics confirms this intuition with precise mathematical detail. We know exactly which nuclear reactions created which elements. We can trace the pathways from primordial hydrogen through stellar fusion to biological incorporation. The recipe for a human being is absurdly complex. Tens of trillions of cells, each containing billions of protein molecules, each protein built from thousands of atoms arranged in precise sequences. But that recipe uses ingredients we can now trace back to their sources: hydrogen from the Big Bang, carbon from red giants, oxygen from massive stars, calcium from supernovae, iron from stellar catastrophe. As your breathing slows and deepens, as your body settles into rest, you might reflect on this. You are the universe's way of knowing itself. The atoms that were created in stars, scattered by explosions, mixed by galactic dynamics, condensed into planets, and organized by evolution into living systems, have, in you, become conscious. The cosmos has arranged some of its matter into a pattern that can think, feel, wonder, and trace its own atomic genealogy. Your existence is improbable, but not impossible. It required a specific sequence of cosmic events over billions of years: stars forming and dying, chemical enrichment gradually increasing, a stable solar system forming at just the right moment, a planet with just the right conditions, life emerging and evolving, and finally, consciousness arising. But here you are, proof that this improbable chain of events can occur. And if it happened once, on this planet, it might happen elsewhere in the universe. Other arrangements of stardust on other worlds might also be contemplating their cosmic origins. The human recipe doesn't end with you. You are one iteration in an ongoing process. The atoms you contain will outlive you, will be incorporated into other forms, will continue their cosmic journey. Some of the carbon you exhale might be absorbed by a tree and become wood. Some of the calcium in your bones might eventually return to the ocean and be incorporated into coral reefs. Some atoms might even return to space if Earth is eventually consumed by the aging sun billions of years from now. But for now, in this moment, these atoms are arranged as you, aware, conscious, capable of understanding their own cosmic history. This is the most remarkable thing the universe has accomplished with its simple recipe, creating patterns of matter that can reflect on themselves, that can trace their atomic ancestry back to the Big Bang and stellar cores, that can find meaning and wonder in the realization that we are, all of us, temporary constellations of stardust. The universe's recipe isn't finished. Right now, at this very moment, somewhere in the Milky Way galaxy, a cloud of gas is collapsing to form new stars. In another region, a massive star is entering its final hours before exploding as a supernova. In a distant galaxy, two neutron stars are spiraling toward each other, about to collide and forge heavy elements in their catastrophic merger. The cosmic kitchen remains open, still cooking, still experimenting, still creating new combinations and possibilities from ancient ingredients. And here's what makes this truly extraordinary. We're not just passive observers of this process. We are active participants. Every breath you take, every movement you make, every thought you think is part of the universe's ongoing chemical evolution. You are the recipe in action, matter organized in a way that allows the cosmos to experience itself. If this journey through cosmic cooking has touched something within you, if you've found peace in understanding your place in this vast, ancient process, your subscription and, help us continue sharing these stories that connect the deepest scientific truths to the gentlest bedtime reflections. Let's begin this final chapter by looking forward billions of years into the future to see how the universe's recipe will continue to evolve. Our sun, that steady yellow star that has warmed Earth for 4.6 billion years, is currently about halfway through its main sequence lifetime. In approximately 5 billion years, the hydrogen in the sun's core will be exhausted. The core will contract and heat up, while the outer layers will expand dramatically. The sun will become a red giant, growing so large that it will likely engulf Mercury and Venus, and possibly even Earth. During this red giant phase, the sun will fuse helium into carbon and oxygen in its core, just as we discussed earlier. This helium burning will last for about 100 million years, a brief phase compared to the sun's 10 billion year hydrogen burning lifetime. The sun lacks the mass to proceed beyond carbon and oxygen fusion, so its element building career will end there. Eventually, the sun will shed its outer layers in a series of gentle pulsations, creating a beautiful planetary nebula, an expanding shell of gas illuminated by the hot stellar core left behind. This core, called a white dwarf, will be about the size of Earth, but will contain about half the sun's current mass. It will be composed primarily of carbon and oxygen, compressed to extraordinary densities. The white dwarf sun will slowly cool over trillions of years, gradually fading from white-hot to yellow to red to eventually becoming a black dwarf, a cold, dark ember floating through space. But this final fate lies so far in the future that the universe isn't old enough yet for any black dwarfs to exist. Every white dwarf that has ever formed is still cooling, still glowing faintly. When the sun dies and becomes a white dwarf, the elements it created during its lifetime, mostly helium, some carbon, and oxygen, will be locked inside it forever, removed from the cosmic cycle. But the sun will also shed substantial mass during its red giant phase, returning about half its material to the interstellar medium. This material, enriched with helium and traces of heavier elements, will mix with the galactic gas and potentially become part of future stellar generations. Earth's fate during this process is uncertain. If our planet survives the sun's red giant expansion, and that's a big if, it will become a scorched, lifeless rock orbiting a white dwarf. The oceans will have boiled away. The atmosphere will have been stripped off. Any remaining solid material will be baked at temperatures that vaporize rock. But this isn't the end of Earth's atoms. Even if the planet is destroyed by the expanding sun, its atoms will persist. The iron that currently comprises Earth's core, the silicon and oxygen in its mantle, the carbon in what remains of its biosphere, all of these atoms will be dispersed. Some might fall into the white dwarf sun. Others might be blown away by stellar winds during the red giant phase, returning to the interstellar medium, where they could eventually be incorporated into new worlds orbiting future stars. The atoms that currently compose you will be part of this dispersal. 5 billion years from now, when the sun becomes a red giant, the carbon atoms that are currently part of your DNA, the calcium atoms in your bones, the iron in your blood, all will have been recycled countless times through Earth's biosphere and geology. They might be part of rock formations, might be dissolved in oceans, might be in the atmosphere. And when Earth is destroyed or transformed by the dying sun, these atoms will continue their cosmic journey. It's a peculiar form of immortality. You, as an organized pattern, will cease to exist. But the material you're made of will persist essentially forever, continuing to participate in the universe's chemical evolution, perhaps eventually finding themselves in other solar systems, other planets, maybe even other living things. Meanwhile, throughout the galaxy, the cycle of stellar birth and death continues. More massive stars than the Sun will continue to fuse elements up to iron and then explode as supernovae, scattering their enriched material into space. With each stellar generation, the galaxy's metallicity, its abundance of elements heavier than helium, gradually increases. Currently, the Milky Way forms about 1 to 2 solar masses worth of new stars per year. This is modest compared to the galaxy's peak star formation rate of perhaps 10 to 20 solar masses per year, which occurred about 10 billion years ago. The galaxy is gradually running out of gas to form new stars. Observations of other galaxies at various stages of evolution confirm this trend. Young galaxies observed in the distant universe, which we see as they were billions of years ago because of light travel time, show vigorous star formation. Older galaxies observed nearby show declining star formation rates as their gas supplies are exhausted. Eventually, in perhaps 50 to 100 billion years, star formation in the Milky Way will essentially cease. The last generation of massive stars will explode as supernovae. Medium-sized stars like the Sun will shed their outer layers and fade as white dwarfs. The smallest stars, red dwarfs with masses less than about half the Sun's mass, will continue burning their hydrogen slowly and steadily. Red dwarfs are the universe's misers, burning their fuel so efficiently that they can shine for trillions of years. The smallest red dwarfs might have lifetimes of 10 trillion years or more. Since the universe is currently only 13.8 billion years old, not a single red dwarf has yet exhausted its hydrogen fuel and died. Every red dwarf that has ever formed is still on the main sequence, still fusing hydrogen into helium. This means that the universe's primary era of element creation, the epoch when massive stars fuse elements and supernovae scatter them into space, is not yet over. We live in what might be called the stelliferous era, when stars are abundant and star formation continues. But this era won't last forever. In the far future, perhaps 100 trillion years from now, the last stars will fade. No new stars will form, because all available gas will have been either incorporated into stars and stellar remnants or ejected from galaxies into intergalactic space. The universe will enter the degenerate era, populated by cooling white dwarfs, neutron stars, and black holes, with no new element creation occurring. But even this isn't the end of the story. On even longer timescales, 10-40 years or more, theoretical physics predicts that protons themselves might decay. If this occurs, all matter as we know it will gradually disintegrate. The white dwarfs, neutron stars, and any remaining cold stellar remnants will slowly evaporate into radiation and lighter particles. This brings us to one of the most profound questions in cosmology. Is the universe's recipe fundamentally reversible, or does it have a directionality? Does complexity increase, persist briefly, then decay? Or might new forms of organization emerge even as old ones fade? The second law of thermodynamics suggests that entropy, disorder, must increase over time in closed systems. The universe as a whole seems to be a closed system, so total entropy should increase. This means that the highly organized structures we observe, stars, galaxies, planets, living things, represent temporary decreases in local entropy, paid for by increases in entropy elsewhere. In the very long term, the universe appears headed toward a state of maximum entropy, sometimes called heat death, where all energy is evenly distributed, no temperature gradients exist, and no organized structures can persist. This fate, if accurate, lies unimaginably far in the future, perhaps 100 years or more. But here's the remarkable thing. We don't live in that far future. We live in the early universe, when stars still shine, when galaxies still form, when planets still coalesce, when life still emerges and evolves. The cosmic recipe is still being executed, still creating new combinations, still exploring the space of possible organizations of matter. And consciousness, awareness, has emerged as one of those possible organizations. The universe has arranged some of its atoms into patterns that can perceive, think, feel, and understand. This might be the most extraordinary outcome of the cosmic recipe. Matter that can contemplate its own existence. The physicist John Wheeler once proposed what he called the participatory anthropic principle, the idea that observers are not just passive recipients of information about the universe, but active participants whose observations somehow help bring the universe into existence. This philosophical position remains controversial, but it highlights something profound. The universe has created in conscious beings something that can observe it, measure it, theorize about it, and perhaps even affect it. You are one of those observers. Your consciousness, arising from the specific arrangement of atoms in your brain, is the universe observing itself. When you look at the stars, you're not just a human looking at distant balls of gas. You're stardust examining its own origins, atoms contemplating the processes that created them. This perspective appears in various forms across human cultures and throughout history. Ancient Hindu philosophy proposed that Atman, individual consciousness, is ultimately identical to Brahman, universal consciousness. Buddhist teachings speak of interconnectedness and the illusory nature of separation between self and universe. Taoist philosophy describes humans as manifestations of the Tao, the fundamental nature of reality. Modern astrophysics arrives at a similar conclusion through different means. There is no fundamental separation between you and the cosmos. The atoms in your body were literally created in stars. The forces that govern stellar evolution govern your biology. The laws of physics that shape galaxies shape your thoughts. Carl Sagan captured this beautifully when he wrote, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." This isn't mysticism or poetry, though it is poetic. It's a straightforward description of physical reality. As you rest, as your breathing slows and your body settles into the gentle rhythms of approaching sleep, you might appreciate the extraordinary journey we've taken together. We started with the simplest ingredients, hydrogen and helium, created in the Big Bang. We watched stars fuse these elements into heavier ones. We witnessed supernovae and neutron star collisions forge the heaviest elements. We saw how these elements mixed through galaxies, how they condensed into planets, how they organized into living systems, and how they eventually arranged themselves into the pattern that is you. The universe's recipe is your recipe. The process that created galaxies created you. The elements forged in dying stars comprise your body. The energy flowing through your cells comes ultimately from the sun, which gets its energy from nuclear fusion, which converts mass to energy according to Einstein's famous equation, E=mc2. Every connection you feel to other people, to nature, to the earth, to the stars, these connections are real and physical. You share atoms with every person who has ever lived. Some carbon atom in your body might once have been part of a dinosaur, a primordial ocean, a tree in an ancient forest, a breath exhaled by someone you'll never know who lived 10,000 years ago. The boundaries we perceive between ourselves and the world are provisional and temporary. You are not contained within your skin. You are a process that extends into your environment, exchanging matter and energy constantly, borrowing atoms briefly before returning them to the cycle. And the cycle continues. Stars are still forming. Supernovae are still exploding. Elements are still being created and mixed. Planets are still coalescing. And presumably, on at least some of those planets, chemistry is still organizing itself into patterns that can metabolize, reproduce, evolve, and eventually think. The universe is still learning what's possible. We represent one experiment in organization, one pattern that happens to be stable and complex enough to persist, to replicate, to evolve, and to develop consciousness. But there might be other experiments, other forms of organization, other ways that matter can arrange itself into entities capable of perception and thought. This is why the search for life beyond Earth matters so profoundly. If we discover that life has emerged independently elsewhere, even if it's just microbial life on Mars or in the oceans of Europa, it would tell us something fundamental about the universe's recipe. It would suggest that the emergence of life is not a unique accident, but a general process, something that happens naturally when the right ingredients come together under the right conditions. And if we eventually discover other conscious beings, other observers, other patterns of organized matter capable of contemplating their own existence, it would confirm something wonderful. We are not alone in the universe's grand experiment. Other arrangements of stardust are also looking up at the stars, asking questions, seeking understanding, feeling wonder. But even if we are alone, even if Earth's biosphere represents the only place in the universe where matter has organized itself into living, thinking forms, that doesn't diminish the wonder. It perhaps increases it. If consciousness has emerged only once, then you are participating in something extraordinarily rare, perhaps the rarest thing in the universe. Think about the improbability of your existence. The specific atoms that comprise you could have been arranged in countless other ways. They could be part of rocks, oceans, atmospheres. They could be scattered through space. They could be locked inside stellar remnants. Instead, they're arranged as you, aware, conscious, capable of understanding the cosmic processes that created them. Your existence required 13 billion years of cosmic evolution. It required stars to form, live, and die. It required supernovae to create and scatter heavy elements. It required galactic dynamics to mix those elements. It required a molecular cloud to collapse at just the right time, with just the right composition. It required a planet to form at just the right distance from its star. It required chemistry to organize into life. It required evolution to create increasingly complex organisms. And finally, it required a specific sperm to fertilize a specific egg, creating the specific genetic combination that grew into you. At every step, things could have gone differently. A slightly different initial conditions in the Big Bang might have created a universe with different physical laws. A different supernova timing might have enriched the solar nebula differently. A different planetary formation sequence might have created no habitable worlds in our solar system. A different evolutionary history might have led to no conscious beings on Earth. A different moment of conception would have created someone else, not you. Yet, here you are. Against astronomical odds, you exist. You are the universe's gift to itself. Matter organized in a way that can appreciate beauty, seek truth, feel love, create meaning, and contemplate the mystery of existence. As your eyes grow heavy and sleep approaches, as your thoughts slow and drift, you can rest in this profound knowledge. You are made of the universe, by the universe, for purposes that might transcend our current understanding. You are temporary but connected to something eternal. You are small but part of something vast. You are mortal but composed of atoms that are ancient and will persist long after you're gone. The cosmic recipe that created you is still being written. New chapters are being added even now, as stars form and die, as elements are created and dispersed, as matter continues to explore the space of possible organizations. You are one sentence in this vast cosmic story, a beautiful sentence, a meaningful sentence, a sentence that adds something unique to the narrative. The universe made you from stardust and stellar ashes. It gave you consciousness so that it could experience itself from your particular perspective. And when your time ends, your atoms will return to the cosmic cycle, perhaps to become part of other stories, other forms, other experiments in organization. But for now, in this moment, you are here. You are aware. You are a temporary pattern in the eternal dance of matter and energy. You are the universe's way of knowing itself, and that is perhaps the most profound thing that can be said about anyone. Sleep well, dear traveler, knowing that you are made of stars, that you are connected to everything, that you are both infinitesimally small and infinitely important, that you are temporary in form but eternal in substance. The universe cradles you as it cradles all things. You are not separate from it, but an intimate part of its ongoing creative process. The recipe of the universe is your recipe. The story of the cosmos is your story. And as you drift into dreams, you carry within you the entire history of existence, from the Big Bang to this moment, from the first stars to your last conscious thought before sleep. Thank you for joining me on this cosmic journey. Thank you for allowing me to share these profound truths about your connection to the stars, your place in the universe's grand design, your role in the cosmos's ongoing self-discovery. As you rest, as you dream, remember, you are stardust that learn to think, atoms that learn to wonder, matter that learn to love. And perhaps that's the most extraordinary recipe the universe has ever created. Until our next journey together, sleep peacefully in the knowledge that you are exactly where you belong, here, now, part of the cosmic story, made of the universe's finest ingredients, a temporary but beautiful manifestation of nature's endless creativity. Sweet dreams, cosmic traveler. Sweet dreams,